Okay. Good afternoon, everyone. So before we get started, let us first offer a prayer for the success of this webinar.
Hi everyone, and welcome to today's webinar entitled Space Weather and Its Effects on Earth. First, let me introduce myself. My name is Julian Delda.
And I am Lord Nico Mendoza from the Space Science and Astronomy section of PAGASA.
We would like to welcome our guests and colleagues that are present here today.
Before we get started, we would like to go over a few reminders for everyone to participate actively in today's event. First, as displayed in the slideshows prior to the start of the webinar, we would like to remind everyone to please mute your microphones, turn off your cameras, and pin the speaker screen once the speaker starts the presentation. This is to avoid unnecessary distractions.
Also, the participants will have the opportunity to submit text questions to our presenter by typing the questions into the question box in the Google Meet control panel. You may send in your questions anytime during the presentation. You will also have the opportunity to ask your questions directly to our presenter. Just raise your hand and state your name and question once we open the Q&A session.
Lastly, we will be providing a certificate of attendance to those who will stay with us until the end of the program. We will be also sending the link of the survey of the presentation. And we would appreciate if you would complete that and provide your feedbacks.
To formally begin our program, let us all hear from Dr. Landrico U. Dalida Jr., PAGASA's Deputy Administrator for Operations and Services, for his welcome and opening remarks.
Thank you very much, Julie and Nico. Good afternoon, everybody. In behalf of our DOST PAGASA Administrator, Dr. Vicente B. Malano, I cordially welcome everyone, especially our distinguished resource speaker for today, Dr. Ernest P. Macalalad of Mapua Institute of Technology, for sparing us his precious time to share his knowledge and expertise in astronomy. I am very delighted for the full participation of our PAGASA officials and employees, especially the Space Science and Astronomy section, personnel of the Research, Development, and Training Division under the stewardship of Dr. Nathaniel T. Bando, and its Deputy Administrator for R&D, Dr. Esperanza O. Kayanan. Also, I would like to acknowledge the attendance of students from Rizal Technological University and Mapua Institute of Technology for joining us today. Hoping for a successful and a fruitful webinar on space, weather, and its effect on Earth. Magandang hapon at maraming salamat po.
Thank you, Dr. Dalida.
Now, without further ado, may we call on Ms. Maria Rosario Ramos, the officer in charge of the Space Science and Astronomy section, to introduce our speaker for today.
Thank you, Nico. So good afternoon, everyone. Let me introduce to you our resource speaker for this afternoon. He finished his Bachelor of Science degree in Physics in 2004, with a specialization in computer electronics at De La Salle University in Manila with honorable mention. As he goes on without leaving the same university, he earned his Master of Science degree in physics in 2006 with distinction. Not only that, he graduated with a degree of Doctor of Philosophy in Space Science in the Graduate Institute of Space Science of National Central University of Taiwan. He is currently a faculty member of the Department of Physics at Mapo University in Manila. He has a lot of teaching experience in physics, such as university physics, advanced courses in physics, to name a few. He is also a faculty in charge of Bachelor of Science in Physics and its double degrees in Electrical Engineering, Electronics Engineering, and Material Science and Engineering. He is a research and development leader of the Center for Astronomy Research and Development of the Rizal Technological University. The program is funded by the National Research Council of the Philippines, NRCP, and part of Science for Change program of the Department of Science and Technology. His previous his previous affiliation is as a visiting lecturer in De La Salle University in Manila, assistant professor, De La Salle University, Dasmariñas City. He also attended numerous schools and workshops internationally. Some of his works were given an award. One is a Golden Award for his work on online application of Taiwan ionosphere model for single frequency GPS positioning. That is in 2011. An innovative mention award for the development of a low-cost sun photometer tracking and data acquisition system in 2004. He is also a member of various associations. Association, the Filipino Scholars in Taiwan, in which he is the founding president, International Global Navigation Satellite System Society Incorporated in Australia, American Geophysical Union, Samahang Pisika ng Visayas at Mindanao. Without further ado, colleagues, friends, please join me in welcoming Dr. Ernest P. Macalalad.
Okay, good afternoon, guys. So I'm Ernest Macalalad
Good
of
afternoon,
Mapua
sir.
University. Yeah. So if I could share my screen right now, is it okay?
Yes.
Okay, good. Okay. Thank you for that kind introduction, ma'am. No? So I will share my screen now. Can you see my screen?
Yes po.
Okay, very good. Okay, so this is my first time giving a lecture slash webinar, no? And I thank Pag-asa, especially the space science and astronomy section, for inviting me to have this webinar with Pag-asa. Okay, so today I'm going to present to you space weather and its effects on Earth. Hopefully, I would be able to finish this on time so that we have a lot of time to discuss any possible future collaboration between my group and with your section, hopefully. But anyway, so let me just first review, especially for those who are not in this field, what is space weather. Okay, so as an overview, space weather is just like your terrestrial weather. It's basically states what the current status of the space between the sun and the earth. So what we're talking about here is how the conditions vary based on the activities of the sun and how it affects the space environment between the sun and the earth. When we talk about space weather, we also talk about how this environment influence the performance as well as the reliability of several or certain technologies that are dependent on the space environment, specifically those space-based instruments like our spacecrafts or satellites, as well as our ground-based technological systems, such as our GPS positioning, our GPS receivers on our phones, communications, uh, power grids, among others. So we talk about space weather, we always start with the description of the sun, specifically the what happens on the surface of the sun. So that includes sunspots, coronal mass ejections, as well as solar flares and solar winds. So we're going to talk about these things in more detail later. Then how these things affect or travel through the interplanetary space. So that's the space between the sun and the planets, as well as how this energy sources affect the Earth's configuration, specifically the Earth's magnetosphere, as well as the Earth's near Earth surface. So one of the effects that we're going to talk about here would be how these things cause solar radiation storms and geomagnetic storms. And all these things that we're going to talk about today will be based on the idea that these things are based on how plasma between the sun and the earth are affected by several factors. So this figure shows the two main plasma parameters that we're going to talk about later, and that is the plasma temperature and the number density. So this number density and plasma temperature are two basic plasma parameters that we're going to talk about, and that will determine whether that the measurements that we have come from are in terms of solar wind, or are they aurora, or are they coming from the solar corona. So plasma is governed not only by your basic physics, but more importantly by electrodynamics and plasma physics. So in the next slide, I'm going to show you some exotic equations, but wag po kayo maglala. So we're not going to talk about too much about these equations, but what we're going to do here is I'm going to give you some basic ideas and based on the equations that I'm going to show to you in the coming slides. So right now, so ngayon po, we are going to talk about very basic electrodynamics and plasma physics so that we are more or less properly guided on how we're going to understand certain aspects of space weather later on. Because we're going to talk about, ano kasi dito, we're going to talk about plasma. So plasma is an ionized gas. So this is gas that is ionized, coming and this ionization is coming from certain sources like energetic electromagnetic radiation from the sun, as well as other energetic particles. So the behavior of this kind of gas, which is governed not only by your usual physics, your forces, it is also governed by concepts of electricity and magnetism, as well as fluid dynamics. Unlike when you're talking about typhoons, wind, etc., we're only going to talk about neutral fluids. For when you talk about space, we're going to look into charged fluids. So that means this plasma, so this ionized gas, do behave according to the equations of electrodynamics. And the four basic equations of electrodynamics are the Maxwell's equation. So this is Gauss' law. The first equation is called Gauss' law. The second equation just tells you that there is no magnetic monopoles. The third equation is called the Faraday's law. And the fourth equation is called the Ampere's law. Again, don't dwell too much about the complexity of the equations, but what do this equation basically mean? So the first two equations basically mean that the electric fields are produced by charges. Okay, so this rho and q represent charges. So this is represented. So in our context today, these are the density of the plasma. Okay, the second equation just tells us that magnetic field lines always form closed loops. So that means magnetic field lines always emanate from one polarity, and it always closes down to another polarity. just like your horseshoe magnet, just like your bar magnet. Okay, so that means the second equation just tells us that uh, when we talk about magnetism, we always talk about two pairs. So we have your south and north poles. So those are two opposite polarities where where in your magnetic field lines emanate from. And this is very important because when we talk about sunspots, so sunspots are basically manifestations of the magnetic activity of the sun. The third equation, Faraday's law, just generally tells us that if you have a changing magnetic field, if the magnetic field changes, like the Earth, like the magnetic field of the Earth, if the Earth's magnetic field suddenly changes, so that induces an electric field, okay, or electric current. So this is the basic idea of the third equation, which is Faraday's law. And this is the same idea, or this is the same concept uh, that governs the generation of electricity from dynamos, for example. The third one is a magnetic field, on the other hand, is produced by two things. They can be produced by currents, just like the Earth's magnetic field. The latest theory right now is that the magnetic field of the Earth is caused by the motion of the molten core, which are basically made up of charged particles. So this movement of charged particles within the Earth's core are believed to be the one that produces the Earth's magnetic field. So this is the basic idea. Also, if any changes in the magnetic field produce electric field, the same goes on the reverse. So that means any electric field changes also affects the magnetic field. Okay, so those are the basic ideas when you talk about Maxwell's equation. The generation of electric field due to charges, the presence of polarities in terms of magnetic polarities, the production of electric field due to changes in the magnetic field, as well as production of magnetic field due to currents or moving charges, as well as changing electric field. And if you combine these four under certain mathematical computation, we actually produce the wave equation for electromagnetism. And that proves the presence, or that proves the existence of electromagnetic waves. So electromagnetic waves were already predicted by this Maxwell's equation even before the discovery of these things. But basically, Maxwell's equation is the reason behind the existence of electromagnetic waves. So electromagnetic waves can range from radio waves, which are the longer wavelengths, up to gamma rays, which are the most energetic and highest frequency of them all. Okay, so this electromagnetic spectrum is based on these four equations. Okay, so as mentioned here, electric fields are produced by charges. So therefore, electric fields also affect motion of charges. So in the coming slides, I'm going to talk about how these charges move in the presence of electric and magnetic fields. So let's start with the presence of a magnetic field. So we already know from our basic physics course that electric charges moves in circles under the influence of a magnetic field. So we call this the gyro motion. So or cyclotron motion. Okay. If we have, for example, a generic direction of magnetic field, the more or less the magnetic field will cause this charged particle to move in a spiral form. So when a charge is trapped within the Earth's magnetic field, they do not move along the direction of the magnetic field straightward, but they circle around the direction of the magnetic field, just like this one. Okay, like this one. Okay, so they move along the direction of the magnetic field, but they also circle around it. So that's gyro motion. Okay, so that's the first kind of motion that this charged particle coming from the sun, going to our atmosphere, going through our magnetosphere. The first motion is called the gyro motion. Now, because, for example, we know that the Earth's magnetic field is not uniform, like unlike this one. So they are much they have a strong intensity near the poles, and in the equator they are relatively weaker, and the direction of the magnetic field is also different. Above the equator, it's parallel. On the pole, it's vertical. Okay, so because of that, the charged particle that is in this magnetic field lines also do some kind of bounce motion, and that is due to the, for example, differences in magnetic field intensity. So this is your magnetic field lines. Okay, so this just tells us that in this region, mahina yung magnetic field. In this region, malakas yung magnetic field. So imagine this is the magnetic field near the equator or around the equator. This is the magnetic field around the poles. Okay. So as I mentioned earlier, the presence of a magnetic field, this charged particle move in circles. So umiikot po siya around this magnetic field lines, like this one. But because the intensity changes, therefore the direction as well as the radius of that circular motion of the charged particle also follows this configuration. But at a certain point, okay, under certain condition, this circling around will actually make this configuration of the Earth's this magnetic field will cause this charged particle to actually stop momentarily at a certain point, and then it will reverse its direction. Okay, so this is what we call your mirror point. Okay, so under certain conditions, these electric charges will actually move in circles, but they will also bounce off a certain mirror point, and of course under certain condition. And what is the consequence of this? So for example, if we have this kind of configuration, okay, let's say this is the magnetic field configuration in the South Pole, and this is the magnetic configuration in the North Pole. So, and then this is the magnetic configuration in the equator. What will happen to this charge is that they will bounce from one point to another. So if we have a lot of charged particles, what will happen is that this charged particle, collectively known as plasma, will be trapped in this region. And this is one of the reasons, and this is one of the mechanism behind the presence of the radiation belts in the Van Allen region. Okay, yung trapped charge particles in the Van Allen belts is because of this bounce motion. So aside from this, because remember that the Earth is also rotating about its axis. So that means the magnetic field that it produces also moves around it together with it. So what happens is that, so what happens is, aside from bouncing off these mirror points, aside from the gyro motion, these particles also drift depending on certain configuration. But the point is that they drift according to the direction of the electric and magnetic fields, depending on the curvature, how the magnetic field changes, as well as the orientation of the magnetic field and the electric field that is produced on the Earth. The point is that they drift. Okay, so these are some of the basic ideas behind the existence and behind the behavior of plasma in these kinds of region. Okay, so just to summarize, first part, things to remember. Number one, moving charges produce electric and magnetic fields. Okay. Next, changing electric fields produce magnetic fields, and then changing magnetic fields produce electric fields. Okay, so please remember this. Also, the Maxwell's equation predicts that the existence of electromagnetic waves, and it moves at the speed of light in vacuum. So that's 3 times 10 to the 8 meters per second. Okay. Also, electric and magnetic fields cause charged particles to, number one, they gyrate, so they circle around. They also bounce because of that difference in magnetic field intensities and direction, and they drift. So these are the things that you should be remembering for now. Okay, so these are just basic ideas, and this hopefully this will help us guide our discussion later. Okay, so what are the space weather effects? Okay, unlike our terrestrial weather, your typhoons, thunderstorms, etc. So kanina nagkaroon po ng nagkaroon ng thunderstorm warning ang Pag-asa, and it was felt here in Cavite. I thought nagkakaroon pa ng disruption, no? Others say, you may agree with me that terrestrial weather is actually high risk, high impact effects. Okay, but space weather effects may not have a high risk, but the impact would still be strong. Okay, so here are some of the space weather effects that we would like to study. So, of course, you have your atmospheric effects. So that's your aurora borealis. So aurora, the presence of aurora in the north and south poles are actually space weather manifestation. Okay, atmospheric effects of space weather. Aside from this, there are a lot of space weather effects, especially on technology. So they can induce radiation damage. They can do some damages in the solar cells and in satellite performance. They can affect accuracy on navigation. They can cause interferences in signal, or they can cause disruption in signal propagation through the atmosphere or through the ionosphere. They can also induce electromagnetic field on the ground that can affect power grids, for example. We call that the geomagnetically induced currents. They can also do some disturbance in high frequency radio waves or other frequencies. So these are some of the common effects of space weather, though they may be low risk because these effects have a relatively low probability. But when an extreme event hit us, the impact is very high. In fact, in recent studies, in recent cost-benefit analysis for example, by the European Space Agency, okay, they did a space weather cost-benefit analysis in 2016. While most solar events and the resulting space weather have little or no effect here on Earth, no, not much, okay, especially for health, example, or this, let's say, for example, damage to property, like what typhoons are doing. But based on a recent ESA study, European Space Agency study, they estimated that the potential socioeconomic impact of these kinds of event in Europe, if it hit today, from a single extreme space weather event, similar to the Carrington event that happened in before the turn of the century, okay, they could cost about 15 billion euros in Europe alone. So if that's the cost of an extreme space weather event in Europe, you could imagine how much effect it has globally. Okay, another study that was mentioned before, in the US, it may cost about $1 trillion of world economy if a certain high impact space weather event hit the Earth without any preparations. Okay, so that's why it's very important to look into these kinds of effects. So just to give you an idea, just to give you a more detailed description of how these space weather events disrupt. Okay, so I put in here a summary of the usual hazard and impact of certain space weather events and certain solar activities or solar events that may happen. For example, if you have a solar flare, in July 3, last July 3, we have our first X-class flare happened for this current solar cycle 25, last July 8, last July 3, it was an X 1.3, if I'm not mistaken, no? X 1.3 class flare is the highest so far in the current solar cycle. Just to compare that to the last solar cycle, the largest X-class flare happened, last solar cycle happened in September 2017, and it was about X9 class. Okay, so for example, if there is an event called the solar flare, so this solar flare produces high energetic particles. So what does this do? It increases radiation, and then its impact would be there may be radiation dose and deep charging, especially in satellites, which we are highly dependent on nowadays. So aside from this, we also flares also produce large or extreme doses of X-ray radiation. So one of the effects would be there will be an anomalous ionization in the atmosphere, especially in the lower atmosphere. And if this happens, there will be an abnormal radio absorption. So yung point-to-point ground communication using atmospheric propagation may be affected. So aside from flares, sometimes flares produce a coronal mass ejection. So if this coronal mass ejection happens, not only it produces X-rays, it also produces plasma cloud. And this is a more dangerous one. So this plasma cloud that is produced by a coronal mass ejection can give out high energetic particles, and it can also cause geomagnetic storms. So when you say geomagnetic storms, so this is storms. So when you say storms, diba? Unusual changes, diba? Unusual changes of the magnetic field of the Earth. Okay, so we call that geomagnetic storm. And that's very important. Why? Because not only it can increase radiation or produce anomalous ionization in the lower atmosphere, it can also give out high energetic particles and can also cause spacecraft charging. Okay, so the electronics from satellites can be affected as well. Aside from that, it can also produce increased currents, electric currents in the ionosphere, which will be the main cause of geomagnetically induced currents on the ground, which affects power grids, pipelines, etc. Aside from geomagnetic storm, they can also cause ionospheric storms. So these are now changes in the ion content in the atmosphere, call that the ionosphere. So what's the consequence of that? There may be changes in the electron density in the ionosphere. And one of the main impact of that, it would be radio wave propagation disturbances. So that includes navigation, because remember that, for example, your phones uses GPS for positioning when nagda-drive tayo using Waze or Google Maps. If there's a large changes in the ionospheric electron density, they can affect radio wave propagation. So that means the radio waves that comes from GPS satellites towards our receivers may be affected as well, giving us anomalous or positions with large errors. Okay, which may affect positioning. Okay, especially right now we are moving towards more reliant on navigation systems like GPS. Aside from that, the upper atmosphere may also expand where our satellites are currently orbiting. So when the upper atmosphere expands, it may affect our satellite orbits, which may affect the lifetime of satellites currently orbiting around the sun, around the Earth. So that includes Diwata 1, Diwata 2, those microsatellites that we have, those nanosatellites, and the planned satellite Mula, or Mulat ba yun? Or Mula, yung bagong mission by the Philippine Space Agency. So as our space assets starts to increase in number. So we must take note of how we would be able to protect these assets under under the influence of these kinds of space weather phenomenon. So aside from solar flares and coronal mass ejections, and especially during solar minimum or quiet suns, corona holes can also uh, pose some danger to or some space weather effects, because corona holes are actually windows of the sun wherein high solar wind, fast solar wind would emanate. Just like when you open your window, so minsan 'di ba pag mahangin sa labas and then you suddenly open your window, yung hangin sa labas na mababilis biglang papasok sa kwarto niya. Corona holes are just like that. And those fast moving solar wind contains plasma, so they can produce geomagnetic storms as well. Okay, so not only do we have a lot of hazards during during years of high solar activity, we also have events that may affect us during solar quiet years or days. Okay, so these are just a summary of this typical space weather disturbances. Okay, so let me give you a scenario. So let's say you are an operator of a radio telescope. I think meron na tayong radio telescope, di ba? I think it's in Tanay. So let's say there's a radio telescope in Australia, in Lermont Observatory. So they're getting radio signals from the sun. Okay, and then in March 15, this happened. Okay, when they observe these radio wave data in solar radio flux, they saw a bump at this time. Okay. Now at certain frequencies. Okay. Now, and then they were also monitoring the X-ray emissions of the sun measured by the GO satellite. Okay, and they saw that the solar flux, the graph of the solar flux looked like this. So this is a GOES X-ray flux. So this is an X-ray intensity in watts per square meter. This is a function of time. This is a solar radio flux. This is also a function of time. And you notice that this bump happened at the exact time as this bump. Based on this graph, we can identify this as a solar flare. And this is actually, based on the measurements, this is actually a very strong C class, bordering on the M class level. So this is a relatively strong flare, C class flare, and this C class flare produced a solar radio burst. This happened in March 15, 2015. Okay? Now, when you're monitoring the sunspots, I think Pag-asa also monitors sunspots. They do sunspots monitoring every day at, I think, 8 a.m., di ba? Okay, so I think you're still drawing sunspots, no? Tama po ba ako? Anyway,
Yes,
so when you
Papa.
saw the sunspots drawing, you can actually see the several active regions here. Okay, and then when you look at a satellite image of the sun, at this moment, you can see these dark spots. These are your sunspots. Let's zoom in. Okay, and then when you look, this is the continuum spectrum of the sun. More or less, this is how the sun would look like visibly. And then you can also look at the magnetogram, how the magnetic configuration of the sunspots. And you will notice that there is visibly black, visibly black and white regions here. So basically, when you look at the magnetogram, black and white, this tells us that they're oppositely, their magnetic polarities are opposite. So this increased activity in the sun's magnetic field is actually due to these sunspots. Okay. Now we can actually look at this also at different wavelengths in the extreme UV, which is also produced by satellites that are currently in space. So this is a picture of the sun at this moment at the 304 angstrom wavelength. So this is extreme UV. This is at 194, and this is at 131 angstroms. And we all notice here that there is an increase. Okay, there's an increased emission of extreme UV at the active region, at this active region. Okay, so this is X-ray, this is extreme UV, this is magnetic field, this is visible lights, and this is your drawing. This is radio wave. So you will notice now at different a single event, a single event can produce a lot of electromagnetic waves. Increase in X-ray emissions, increase in radio emissions, increase in extreme UV emissions. Okay, and when we try to animate this, try to have a series of pictures and animate this, it would look like this. Okay, so this is wait. So if you're going to animate this, you can see this is your active region. I'm not really sure what active region is this, but this is your active region. And when I play this, you will notice that increase in that one. Okay, so if you're going to pause this, so this brightening of that region is the one responsible for this increase in X-ray and increase in radio. Okay, so this is a solar radio burst. So by the way, this data came from the Solar Dynamics Observatory. You can download this data from this website as well. So this is what I'm going to do today, no? Yung mga data, most of the data that I'm going to show you, I will be providing you the link where I got these kinds of data. Okay, so that you can have some idea kung saan pwedeng makuha yung mga data, which I'm sure some of you are already familiar with. Okay. Now, this is the X-ray C-class solar flare that happened in March 15. Okay. Now, not only did this active region produce a solar flare, it also produced a coronal mass ejection together with it. So usually coronal mass ejection are observed using the large angle spectrometric coronagraph, which is produced by the Solar and Heliospheric Observatory, or SOHO. So you can get this from this website or from this website. So this is the LASCO image of this CME. So if you're going to play this, you will see that at 2 UT. Okay, so we can go back here, so we can see that this coronal mass ejection happened at around 1 or 2 o'clock in universal time. Okay, so this is your CME. So this is a very, very large CME. In fact, this event is what we call this. It caused a very strong geomagnetic storm. Okay, the flare may not be as strong as X-class flare that happened last July 3, but nevertheless, this still produced a very large coronal mass ejection that caused the strongest geomagnetic storm in the past solar cycle. And we call this St. Patrick's Geomagnetic Day, St. Patrick's Day of 2015 Geomagnetic Storm. This is a summary from the National Weather Service of NOAA. So this is a G4 level geomagnetic storm. These are the conditions. So this storm have the duration of about 18 hours, so almost a day, very long day. So the magnetic field is the strongest for the current solar cycle. Out of the 5 G4 storms last solar cycle, 5 lang yung G4 storm. No proton and electron and radiation enhancement with its storm, which is unusual. And it is caused by your coronal mass ejection that you saw earlier. These are the impacts. Those are they produce geomagnetically induced currents, although no power failures reported to date. Yeah, and then there were severe electron density depletion in the equatorial regions. There were aurora in Michigan, which is rare, to Alaska, and then as far south as Colorado in March 15. So when they forecasted this, the CME actually arrived 15 hours earlier than it is forecasted. So you will notice here that the forecasting this kinds of event is still very hard. Okay, so I will show you some examples later as well. No? How how arrival of these kinds of these events actually is very difficult to forecast. Okay, so let's go back to our data. So this is our data. So this is actually one of the most famous events that happened in the last solar cycle 2024. So see, I also have a paper looking at this event and its effect on Earth, so in the Philippine coast, in the Philippine region. But let me give you an example. So this paper is actually a paper entitled Ground Geomagnetic Field and GIC Response to this to the March 17, 2015 storm, published in Earth, Planets and Space last 2018. So this is an example of some of the graphs that we usually use to identify geomagnetic storms. So by the way, again, this set of graphs on your right, on your left, are graphs or images that describe the solar storm. And then the effect on Earth is they produce a geomagnetic storm. So when you talk about geomagnetic storm, we always look at the plasma that the storm the plasma that caused that geomagnetic storm. Because remember, charged particles affect magnetic field affects charged particles. So that plasma that came from the Earth, that came from the sun, nanggaling siya from the sun in the form of the solar wind. So that means we need to look at solar wind parameter. Solar wind, as you saw earlier, is a plasma. So that means when we describe plasma, we have to describe them in terms of density, plasma density. You can also look into the magnetic field it carries. We call this the interplanetary magnetic field. And this magnetic field is the one that interacts with the Earth's magnetic field. Okay. Next would be the speed of the solar wind. Okay, typically, nasa 450 kilometers per second ang solar wind normally. But when it is enhanced like this, for example, due to a coronal mass ejection, it would reach to about 500 to 600 to maybe 700 kilometers per second, almost as twice. So this is a very high-speed solar wind, and it caused a geomagnetic storm. Now, how do we measure now geomagnetic storm? We use geomagnetic field indices or geomagnetic indices. So this data is came from Kyoto University World Data Center on geomagnetic for geomagnetism. So the first one is your disturbance storm time index, and the second one is aurora electrojet index. But the basic thing is that normally, you will notice before the storm happened, ang DST index about this level. But when the storm happened, you will see those weird changes. Okay, so later I will describe to you how we read this. This is also AE index. So we notice that from normal levels, it actually produces large fluctuations in the Earth's magnetic field. So these two are just two of the many indices we use to describe geomagnetic storms. And the effect would be a geomagnetically induced currents. This is in amperes. So we'll notice here that this is measured by magnetometers from the ground station. Okay, so remember when changes in magnetic field produces currents, and then those currents will affect the currents that are in the power grids. So for example, these are the induced currents due to the changing magnetic field brought about by this geomagnetic storm. So this changes is the one that is measured, and this will quantify how strong the GIC is at this station. So this is very important. This is one of the these are one of the important effects of these kinds of storms. Okay. So again, in summary, we have your solar storm. You have and then this solar storm produce a geomagnetic storm, and the effect would be there was a geomagnetically induced current on the ground. So this is usually what the whole story is. Start with the sun, and then what is its effect on the earth. In this case, the effect on the ground current. Okay. So that's why several countries have set up their own space weather monitoring systems. Of course, one of the primary agencies would be the SWIPC, or the Space Weather Prediction Center, operated by NOAA and the National Weather Service. This is US. So most of the products produced by the space weather community is actually produced by the Space Weather Prediction Center. Okay, of course, there are data sets that can be locally produced depending on the country. For example, you look at the Japan space weather forecasts. So this is operated by Japan. So they have, aside from the products produced by the Space Weather Prediction Center, SWIPC, they also produce their own products using their own instruments. Okay, not only the rich countries have this one or are invested on this monitoring, even our neighbors like Lapan, Space Science Center of Indonesia, is also operating their own space weather forecast systems. Not only Indonesia, Malaysia also produces their own space or monitors their own space weather. So hindi malayo tayo din, no? Kasi if they are, for example, if they are invested on this, why not? We should also invest in these kinds of systems, no? Though they have, sabi ko kanina, though they have low risk, but they have high impact, especially for us that we have increasing dependence on satellite technology. So aside from government agencies, there are also very good civil organizations that also monitor space weather. We have Space Weather Live. Ito isa sa mga pinakagamit kong ginagamit na website, Space Weather Live. So all of the data that they produce or they wish that they publicize or publish in their website are coming from space agencies from let's say from the US, from ESA, etc. Other communities that are very invested on space weather monitoring are ham radio operators. So Solar Ham is a good website also that monitors or that they actually collates space weather products that are related to operation of amateur radio, yung mga HF radio operators. Okay, so these are some of the resources that we could use or for visualization as well as for data. Okay. Okay. So this is just a brief. Don't like this brief, no? Pero almost 1 hour na sasalita. But this is just to give you a context of how important space weather is, especially for us. So let me just talk about a little bit more detail about space weather. Kasi kanina more on pahapyaw lang, no? Just to give you a good introductory context. May parang trailer, kumbaga. Okay, now, when we talk about space weather, we always talk about the space environment. So the space environment we talk about space weather, space environment starts with the solar atmosphere. So what happens on the surface of the sun? Whatever happens in the surface of the sun, it may or may not have an effect on Earth. Because before what happens in the solar atmosphere, it has to travel first in the interplanetary space. If it is electromagnetic in nature, it will travel only for about 8 minutes to reach the Earth. But if it is plasma-based effect or event like CME or enhanced solar wind from solar corona holes, they travel for 1 to 3 days, maybe 5 days. Okay, so it depends on how the Earth is positioned with respect to the sun. So it's a matter of a lot of factors. But as an event travels from the sun to the Earth, it will encounter the Earth's protective bubble called the magnetosphere. Okay, because of the Earth's magnetic field. So this magnetic field protects us from the magnetic field that is carried by the solar wind. And then on a more grounded aspect, this whatever effect or whatever event that happened in the sun, it may reach the atmosphere, producing the ionosphere. So one of the most famous effects would be your aurora. So this is how usually space weather is being monitored. I myself personally, I'm more invested in how space weather events affect the local ionosphere in the Philippines. So most of the researches that I have are based on the fact that any space weather effect may have an effect sa ionosphere which would directly affect several applications such as communication, navigation, aviation, and even geomagnetically induced currents. Okay? So yun. So let's start with solar atmosphere. Just a quick overview. So when you say solar atmosphere, all events come from the sun, and the sun produces most of the energy that we receive on Earth. There are two types. The first type is our steady energy radiation. Ito yung usual. Ito yung day in, day out. Ito yung laging binibigay. So this steady energy radiation can be of the form of your electromagnetic waves. So that will give us the date in terms of measurements or in terms of physical quantities. On the Earth, we usually measure that in terms of irradiance. So these are electromagnetic waves coming from the sun. So they can be of the form of visible, UV, IR, that they penetrate the Earth's atmosphere. Aside from electromagnetic waves, light coming from the sun also produces particle radiation. We call that particle radiation. It's a continuous one, no? It's a continuous one. We call that the solar wind. Okay? So this solar wind, just like any wind, flows from one point to another. In this case, this flows from the sun towards the Earth. Now, because again, solar wind is plasma, so they move. Moving charges produce magnetic field. Remember? So these moving charges produce magnetic field, and we call that magnetic field the interplanetary magnetic field. And because that magnetic field produced by the solar wind is magnetic in nature, it will interact with the Earth's magnetic field. On the first approximation, the Earth's magnetic field, without the sun, without this, is a dipole. Okay? So once the interplanetary magnetic field interacts with the Earth's geomagnetic field, what will happen is that because this solar wind is continuous, lagi may solar wind, okay, on the solar wind. So it continuously pushes the Earth's magnetic field on the day side, flattening it on the day side, and at the back side, it elongates. So later, I will describe to you basic description about the Earth's magnetosphere. But the point is that because of the continuous bombardment of particle radiation, these are steady particle radiation, the magnetic field of the Earth, including the magnetosphere, forms a bow shock. or a shock wave. Just like your shock wave when you have a supersonic jet flying through the atmosphere, flying through the air. So this bow shock is the same as this bow shock. Okay, this is continuous. So that means any changes in the solar wind will change the configuration of the Earth's magnetic field. Again, changing magnetic field produces currents on the ground. Okay? Typical values ng magnetic radiation, particle radiation coming from the solar wind. Speed 400 to 450 kilometers per second. If there's a solar wind, that's normal. If it is increased, that's an increased solar wind. So it may affect our magnetic field. Number density is about 7 million particles per cubic meter. Temperature is about 100,000 Kelvin, and the magnetic field is about 7 nanotesla. So these are the typical values of your solar wind. Anything that deviates from this significantly, something significant will also happen on the Earth. So these are your continuous energy radiation, electromagnetic and particle radiation. Now, if events happen on the Earth, we call on the Sun, that is not normal, we call that transient energy radiation. They can be of several forms. For example, if electromagnetic waves is the one that changes rapidly, what will form is a solar flare. If the solar wind changes, it can be due to high energetic particles caused by a CME or plasma clouds. So these are the three most common sources of this transient radiation: solar flares, coronal mass ejections, and corona holes, where your high-speed solar wind may emanate from. Okay, so meron kang steady, meron kang transient. When you say transient, ito yung pansamantala. Okay, pansamantalang big burst, hindi siya yung normal. Now, to look into these things, we usually see the sun with different eyes. So from our one of my first few slides about yung electromagnetic spectrum. So the sun produces these kinds of energy. So that means we can look at the sun at different wavelengths. So this is an example of the products produced by the Solar Dynamics Observatory. This one. Another satellite can also be used, the Solar Heliospheric Observatory, or SOHO, though they produce more or less the same set of data, but sometimes they have different wavelength sets, different sets of wavelength. So these are the sources of your data. Okay, so these are some of the products. This is Dopplergram. This is how the surface of the sun moves. This is magnetogram. So this gives you the magnetic polarity of the surface of the sun, or the photosphere. HMI continuum. This matches the visible light. So we look at this visibly to look at the photosphere. And then this is we use this wavelength, 1,700 angstrom, to study the photosphere, 4,500 for the photosphere, and a different wavelength. So different wavelengths. For example, if you want to observe the corona holes, we don't use the, let's say, this data or this product or this product. We actually use the 193 angstrom, because this is the one that we use. This is the wavelength wherein your corona hole emits less. So at this wavelength, corona holes emits less radiation, just like what you saw here. So this is at 193 angstrom, because corona holes do not emit much of this wavelength, 193 angstrom. They will appear dark at this wavelength. So that's why we can see corona holes at this wavelength. But for example, if you want to look at solar flares, we look at the sun at 131 angstrom, and maybe shorter wavelength than that at 93 angstrom. So we use these products to observe solar flares. So just like this one. So this is a solar flare, and this is observed at 131 angstrom. So depende sa gusto nyo makita. Okay, so the rest. And then if you want to observe active regions, you look at this 221, 355, and even 193 angstrom. So depende, no? Depende sa gusto nating makita yung product na gagamitin natin. Okay, now as I mentioned, last July 3, there was an X-class flare happen at this point. So you will notice here, etong two regions at two wavelengths na to, 94 at 131 angstrom. Ikakita nyo rito, no? Yung pag, okay, let me go back again para mas makita natin. So you will notice here, magkakaroon ng bright, biglang, kita nyo, yung biglang flash. So that's more obvious in this wavelength, although sometimes they can be observed in other wavelengths. But most of the time, we observe we observe solar flares using these wavelengths. And then that is actually seen, the active region where it came from can actually be seen in this magnetogram, but not so much with the HMI continuum. Okay, so that's it. So that's how we usually see the sun at different wavelengths and different other products of the Solar Dynamics Observatory. Okay, now solar atmosphere. When we talk about solar atmosphere, we talk about the solar corona. So that's this is the visible light produced by the corona that can be seen only when we have a solar eclipse. So this is solar corona. So these are solar winds. Okay, so it contains about extremely hot gas, and that is in plasma form. So they stream outward in all directions in the sun. But when we have a corona hole, what will happen is that the corona, when we have a corona emits X-rays. So this is the sun today. Right now, it would look like this. So sa mga nagtingin ng solar sunspot, nakita nyo to, di ba? Tama ba ako? Nakita nyo itong sunspot kanina? Assuming na clear yung sky, no? But anyway, so you can see the sunspots. Now, as mentioned here, if you want to look at the corona holes, we look at this wavelength at 193 angstrom. So this active region, this visible sunspot, and actually visible din dito, if you can see it here, no? This, and this, no? Can actually see this active region and this active region. And we look at, if we use the 193 angstrom, it would look something like this. Okay, so again, this is kanina lang. So this is the active region that you saw earlier, and there's another active region here. There are some active regions here that are not visible in this spectrum, but we can actually see it here. But more visibly, we can see at this wavelength the presence of the corona hole because of the lower density than average. So that means at these points, we have less emissions of X-ray and extreme UV, so that at this wavelength, at 193 angstrom, it would look dark. And these corona holes are sources of high-speed solar wind. Okay. A few days ago, there was an alert made by Space Weather Live over Twitter, wherein, remember this corona hole? This corona hole is actually rotated from a few days ago, from this one. Yung corona hole kaninang ito, this corona hole is actually looks like this 5 days ago, July 10. Okay, so medyo automated na si Space Weather Live because what they did is they made a corona hole map to determine if the size of this corona hole is large enough to produce enhanced solar wind. So the enhanced solar wind, estimated time of arrival is about 3 days. Okay, so that's the forecast, unofficial forecast of this civil civilian organization. And then earlier, pagising ko kaninang umaga, I received a alert also from Space Weather Live, and they said that currently we have an active geomagnetic field. So that means this enhanced solar wind arrived actually 5 days late than forecasted, and it affected the geomagnetic conditions or geomagnetic field. So right now, we are on active conditions. I'm not sure at this moment if this changed a bit. No? So later siguro we can check. Okay? So this is an example of uh, paano ba dito? Popularizing solar weather as space weather um, uh, information. Okay? So if you have Twitter, you can actually follow Space Weather Live. So they have a lot of information, or you can go to their website as well. Okay, so that's it. That's for your solar corona. So corona holes are usually are more evident, or they frequently affect the Earth and produce enhanced solar wind. Usually used during solar minimum or low solar activity. Because remember, when you have a high solar activity, more sunspots formed in the solar atmosphere, thereby lessening the space for these corona holes to form. Speaking of solar activity, we already know that solar activity is mainly measured in terms of the number of sunspots in the sun's surface. So I chose this sunspot, this date, January 6, 2014, because it has a very, very large sunspot. Active region 1944. Okay, so to give you an idea, relatively, this is the size of the Earth, and this is the size of the Jupiter. So you will notice here that this main region, main sunspot, yung parang ano ba tawag dito? Siguro we could call this mother sunspot. It's about maybe around 10 times larger than the radius of the Earth. And it's so big that they can actually be seen by your usual telescopes, no? Ganon siya kalaki. And then when I tried to look for sunspot drawing, kung may sunspot drawing ang Pag-asa for this, you can give me para mas updated yung slides ko in the future. But anyway, when I looked at the sunspots drawing near to us at Western Australia at Learmont Observatory, they can actually see that sunspot. It's a very, very large sunspot. Okay, so this is just an example of how sunspots are usually visualized. So we already know that sunspots are named according to their appearance chronologically. Okay, so if this is 1944, this is 1946, so that means this active region came in first, and then ito yung sumunod. And then itong active region 1945 na to, I think this is already remnants of that large active region before. So ito namatay na, pero ito hindi pa namamatay. Ito pamatay na, I think. And then etc. Okay? So what are active regions? Again, this is just a review. These are regions in the solar atmosphere wherein there is a strong magnetic field. Okay, so sunspots frequently form in active regions, and active regions appear bright in X-ray, just like this one. Okay, they appear in extreme UV and in X-ray. Sometimes they are the main source of solar flares, and sometimes they are the main source of your coronal mass ejection. Although there are certain CMEs that are not produced from sunspots. We call it stealth CMEs, though they are very rare, but they do happen. But most of the time, CMEs and solar flares come from active regions. Okay, so these active regions, the number of active regions changes periodically On the average, they fluctuate. The number of active regions fluctuate every 11 years, sometimes 12 years. No? Around 11, 12 years, and we call that your solar cycle. So this is the latest sunspot number. So right now we are on the start of your solar cycle 25. This is solar cycle 24. Relatively, you will notice here, if you're going to zoom in here again. Okay, sorry. If we're going to zoom here, okay, so this is solar cycle 24. And then this is solar cycle 25. This is the projection or the prediction of this current solar cycle. They are predicting that the ongoing solar cycle 25, is of the same amount or the same intensity as solar cycle 24. But relatively, historically, these two solar cycles are very low compared to the past three solar cycles, solar cycle 23, 22, and 21. Even smaller than solar cycle 20, etc. Okay, this is the prediction. But there are some scientists or groups that predict that this solar cycle will be much higher. Nevertheless, they predict that it will peak at around year 2025. Okay, so the more active the region, the more active the sun is, the higher chances of having solar flares as well as coronal mass ejection. But it's not necessary. Now, the strongest flares and the strongest CMEs will be produced during solar maximum. In fact, last solar cycle, yung solar flare na na-produce, yung largest solar flare na na-produce was produced during the descending phase na ng solar cycle 24. Actually, in almost 2018 na. Itong peak na to, this is actually when the September 2017 flares was produced. So, as you will notice, no, it doesn't necessarily mean na kapag active ang sun, malakas yung X-rays, doon makakaproduce ng malalakas na solar flares. But at the very least, the frequency, the probability of having the solar flares will increase when the activity of the sun is increased. Parang raffle lang yan eh. The more sunspots you have, the more chances that we have these kinds of events. So this is just an example of different dates, the pictures ng sun at different dates at 193 angstrom. This is 2010. So solar minimum, start of the solar cycle 24. And then at around 2014, the peak of the solar cycle, you can see that there are a lot of active regions. And then at 2018, during the descending phase, you can see that the active regions are much less. So you will notice here that the corona holes are more, will form more frequently during low solar activity than high solar activity. Another example or another parameter that we use to measure solar activity is called the F10.7 solar flux. Okay, so these are solar flux units that also follows the 11-year cycle of the solar activity. On the left side, this is a 23 year picture of the sun from 1996 to 2018, covering two solar cycles, solar cycle 23 and solar cycle 24. Now, this picture is obtained from the Hinode satellite. Okay, so that's another mission, a satellite mission that observes the sun. I think it was decommissioned already, but the data from the Hinode satellite is still available. Okay, so you will notice here that active regions, actually they say that the actual solar cycle is twice of this, about 22, because yung during this time kasi nag-flip yung magnetic configuration of the sun. So let's say if this is upward, then it will be it will shift to downward, and then it will shift back to upward, or something like that. But we usually name solar cycle during that 11-year cycle only. So kung gusto nyo maka-observe ng solar flares, more solar flares, we can observe that maybe we start observing it more and more start of 2022, maybe 2023, and it will start to decrease at around 2030. And it's projected to end on 2033. Okay. The start of the solar cycle 25 was actually announced last year lang by NASA and NOAA satellites. So officially, it started, it started December 19. Yeah, December 19. Officially, it started, and it will peak. It is expected to peak at around July of 2025, and maybe end on 2033. So yeah. Now, as I mentioned earlier, sunspots are regions of high magnetic activity of the sun. So if we're going to draw the magnetic field lines of the sun, it would look very complicated like this, unlike the more or less much simpler magnetic field configuration of the Earth. Okay, so these are magnetic field configuration. So imagine, let's say we have a sunspot pair like this. One is north and one is south. The designation of south and north are arbitrary, so long as one polarity, one region is opposite the other. Okay, so imagine this is a horseshoe magnet. So magnetic field lines would form like this. And then if you're going to take a picture of the surface of the sun at this wavelength, it would look like this. These are not magnetic field lines, but this picture is the plasma trapped in that magnetic field lines. Remember, diba kanina, when we have if the magnetic field lines are in certain configuration, plasma can be trapped in there. So that is what we can see here. Yung plasma, yung light emitted by the plasma trapped in that magnetic field lines. Okay, we cannot actually see magnetic field lines, but what we can see are the particles that goes with it. So parang meron kang bar magnet, and then you place a bond paper sa ibabaw, and then you sprinkle iron filings. So that's how you visualize magnetic field lines. So you put something in that magnetic field, and then you allow it to reorient itself according to that direction so that you can see yung configuration of magnetic field lines. Same goes with your compass. So may compass ka, yung direction of magnetic field lines, that is where your compass needle will align to. So that will help you visualize saan papunta yung magnetic field lines or saan papunta yung magnetic field. So same goes with this one. Okay? So using the Solar Dynamics Observatory, we can actually use the magnetogram. So let's say this example is the HMI continuum data of the sun last September 6, 2017. Okay, so we notice that there are two major active regions, active region 2674 and active region 2673. This is the zoom in case. So if we're going to look at the telescope, they will look something like this. But if you want to know about how active how intense the magnetic field in these regions are, we look at the magnetogram. So this is the magnetogram. So active regions are not only named by their number, but they can also be identified based on the magnetic configurations. So they can be unipolar, so that's alpha, meron kang beta, may gamma, etc. So, and actually, I'm interested to learn from your section, from Pag-asa, ano yung pamantayan on how you identify if it is an alpha, gamma, beta, delta type of active region based on just looking at the looking at the picture. Okay? Or you use this. I'm not really familiar with the process, but at least if you want to know the magnetic field configuration using the magnetogram, we could look at like this. So this is an active region. I think this is a beta. This is a delta. Very complex. So you can use the magnetogram to classify the magnetic configuration of your active regions. Okay. Now, these active regions, as I mentioned earlier, are source of two major solar events, the solar flares and your CMEs. So flares, as I mentioned earlier, are giant bursts of X-ray and energy that they travel with the speed of light, because these are X-ray emissions. So they travel with the speed of light. Given the distance of the sun and the earth, it reaches the earth in about 8 minutes. So almost instant yung effect ni solar flare sa earth. So on your right side is the July 3 solar flare, X plus flare. And on the right, and then the left side, this is the X 9.3 X plus flare last September 16, which came from this active region, 8673. Ayan. Okay. So aside from solar flares, sometimes solar flares produce CME, sometimes not. Okay, and these coronal mass ejections are different in nature because unlike solar flares, solar flares are electromagnetic in nature, CMEs are gas plasma in nature. So when they are ejected from the sun, what will happen is that CMEs accelerate the background solar wind. So if you're going to look at the solar wind data, it will appear as an increase in solar wind. Sometimes it has a quick jump, about maybe, if it reach Earth, it's about maybe by 1.5, 50 times more to 100 times more. Depende sa speed, sa lakas ng coronal mass ejection. But the point is that, unlike solar flares that almost instant yung effect, coronal mass ejection, it may take several days to reach the Earth. So that means we have a leeway or a time to predict how the CMEs will travel sa interplanetary space, and if and when it will reach the Earth, how much of that CME will reach the Earth, etc., etc. Usually, when we look at solar flares, more often than not, merong napoproduce na CME. So this is the CME that was produced noong March 15. So ito yung CME na na-produce during that caused the geomagnetic storm of March 2015. March 2015, the St. Patrick's geomagnetic storm. This is another version of the LASCO image on board the SOHO satellite. So this is the large angle spectrometric coronagraph. Okay, so may nakita kayong red, meron din kayo makikitang blue. So this is how we usually express or observe CME. And sometimes, and most often, we use this to estimate the initial speed of that CME so that we have an idea if and when it arrives on the Earth, when it will arrive. 3 days, 4 days, 5 days, etc. Okay? But because of marami pa kasing nangyayari between that point in time na na-emit or na-eject tong cloud na to, marami pang pwedeng mangyari before it reaches the sun. So that's why yung continuous monitoring of the solar wind is also important. Okay, so let's talk about these two in a little bit more detail and how they are classified. So solar flares are classified based on their X-ray emissions using the GOES X-ray flux. Ito rin po yung GOES satellite na may kamerang nakatapat sa Earth for weather observation. So this is the same satellite. So one product. So meron siyang naka-face sa Earth, meron din siyang naka-face sa Sun. So this goes X-ray. So what GO satellite does is it measures the X-ray emissions from the sun. So these are X-ray emission, and then pag nagkaroon ng flare like this, it will appear as a big increase and then gradual decrease. Big increase and there's a gradual increase. So you will notice here meron dalawang flashes. 1, 2. So yung nakita nyo kaninang dalawang flash, yun. Okay? So depende sa intensity of this flare, we can classify the solar flare. So merong A, B, C. These are your usual classification. Ito yung mga background. C class na mataas, around near 10 to the negative 15 watts per square meter flux. Malakas na yun, just like yung flux na na-produce noong March 13 that caused the geomagnetic storm or St. Patrick's geomagnetic storm. Larger than that, 10 to the negative 5 to 10 to the negative 4, that's an M-class flare. And then X-class flare, strongest of them all, that's the 10 to the negative 4, greater than. So this one, this, and this are X-class flares. Okay? So if we're going to look at the observed solar flares based on their class and try to distribute it year by year, this is an example of that, no? From 2005 to 2017, the blue is the C3 plus, so C3 and above flares na C-class. Green are M-class flares, and then red are X-class flares. So you will notice here that this is solar cycle 24. Solar cycle 24. This is the descending phase of solar cycle 23. So more CM X-class flares are observed during high solar activity, and low observation of these kinds of flares during low solar activity. But again, just like as I mentioned earlier, the strongest solar flare, this is the strongest solar flare last solar cycle 24. It happened in September 2017, during which the solar activity is low. Okay? So hindi porket minimum or mababa ang solar activity, hindi na tayo makaka-experience ng extreme solar space weather event. Okay, sige. Next, coronal mass ejection. So this is an example of a coronal mass ejection. This is hango sa picture. This picture is based from SDO 304 nanometer. So this is an example of a coronal mass ejection emitted by the sun. These are LASCO images. This is August 19 to 20, 2013. This is February 27, year 2000. So these are some images of actual coronal mass ejections. So this is your coronal mass ejection is July 16, 2013. So as I mentioned earlier, diba, sunspots, this is typically how your magnetic field lines would look like. Now, as the sun as this magnetic field region increases in intensity, the extent of the magnetic field lines will stretch like this and will stretch like this until such time that it will twist and turn, forming an X point where we call that phenomenon your magnetic reconnection happen. And when that magnetic reconnection happen, the plasma trapped within this magnetic field configuration will be ejected. That's why it's called the coronal mass ejection. These are ejections of mass specifically plasma from the corona, and then it will produce like this. So I have a simulation here wherein you can see how this CME usually form. Okay. Okay. Are you still with me, Nico? Are you still with me, Nico?
Yes po, yes sir.
Okay, sige. So let me just fast forward this, no? So imagine you have your active region like this. So ganyan yung itsura ng magnetic field line. And then it will start to, as the magnetic field, magnetic activity increase, the chances of the plasma to be to expand like this increases until it will cause a magnetic reconnection like this. So once this magnetic reconnection happens, at this point, energy is an explosion happens, thereby this cloud will now be ejected, and it will travel now in your interplanetary space, and it would look something like this. Okay, so ganun yung itsura. So this cloud of plasma is now traveling faster than the background solar wind. So when we look at the solar wind data later, you will see this as an increase, abrupt increase. Hindi siya gradual increase. It will be an abrupt increase in solar wind density, solar wind temperature, solar wind speed. I will show you later. Anyway, that is how they generally form. Of course, there are some complications in reality, but generally, this is the idea. Okay, by the way, once magnetic reconnection happens, aside from explosion, a particle explosion, electromagnetic explosion also happens. And this is usually detected by spectrograms measured by radio telescope. So makikita to sa radio telescope. Yung explosion na to, madetect niya sa radio waves. So anyway, so now that the CME and the events go to the interplanetary space, so as I mentioned earlier, this is how, if you're going to look at the solar wind data, it would, ng CME, signature ng CME, it would look like this. So this is your typical solar wind speed, as I mentioned earlier, 300, 450. But when the solar wind, when the CME impact the Earth's impact the Earth, it will appear like a jump in the solar wind. So from your typical 400, biglang mag-jump siya to 500, even reaching to about 700 kilometers per second. From your usual 300 to 400. So almost twice yung inabot. So this is a very fast solar wind. This is again the CME that occurred in 2013 and in 2015, March 2016. So the interplanetary magnetic field, so that's a magnetic field that the solar wind carries, also also abruptly changes. The point is that a geomagnetic storm happens if the interplanetary magnetic field points downward. I'm going to talk about more of this later. But anyway, you will notice here that aside from the speed, the temperature of the solar wind also abruptly increases. But not, and then the density also changes as well. Now, this solar wind data is one of the input data that we use to predict when start CMEs will arrive. Of course, including yung initial computation ng speed, your initial speed computed from the LASCO telescope. The point is that they usually put this, NASA and SWIFC, NOAA, put this in a model. The main model that they use is the WSA-LL solar wind prediction model. So basically, this is a solar wind model, and then they tell you using physics-based calculations, they will tell you how a certain event will affect the Earth, when it will affect the Earth, and which part of the which part of the cloud will affect the Earth. So this is just an example. No? The prediction or the forecast was made in March 14, 2015, when the CME uh, when the CME uh, when the CME was formed from the sun, or was ejected from the sun. Then when I play this, this will be simulated, and then about 1 to 4 days yung kanilang prediction. So let me just play this. Oh, so this one is the CME that was produced, the model. So this picture is your background solar wind. This is the background solar wind. And then if you're going to move it forward, you will see the tiny formation here ng CME. So you notice here that the CME that was produced is actually accelerating. So red here means faster speed. Green to yellow to orange, medyo ano siya, slow moving solar. So you notice here that the projection is that this cloud of plasma will hit the Earth at 3:17, 10 UT. Okay, this is the Earth, by the way, the Earth. Okay, so this is just an example. Now, this is the forecast. In reality, it hit at around 17 March, around 2 UT, 2 Universal Time, which is about 8 hours earlier than predicted. Okay, which is what I showed you earlier, di ba? Ang prediction ay darating si CME ng 10 UT, 3 March 17, 2015, pero in reality, dumating siya much earlier. Okay, so you will see here how difficult forecasting these kinds of events will be. It's really, really difficult. Even NASA and NOAA are having a hard time really predicting it on the spot. Sometimes they hit it, sometimes earlier, sometimes they miss it by several days, sometimes they hit it, they predict by ang off ng mga several hours. In fact, may nabasa ko the other day, there was yung tinatawag na Bastille Days geomagnetic storm, yung CME na na-produce exactly 21 years ago. Ang prediction, it will arrive 3 days later pa. Pero naramdaman siya within the day. 1 day lang dumating. So sobrang bilis ng CME. In 1 day dumating yung CME. So that happened in year 2000, Bastille Day. Anyway, so moving forward, so this is just an example of some predictions made by this Space Weather Prediction Center. Okay, so this is the solar wind situation right this week. So beginning July 13, so that's 2 days before. So this is for 24 hours. Ang ending niya ay July 14. So normal ang ating solar wind. Speed is about 350 to 400 kilometers. Density is below 10 particles per cubic cm. BZ is normal. Density is normal. Diba sabi ko kanina, typical intensity ng interplanetary magnetic field is about 7. From that order, no? So total magnetic field is about 5 to 10. So very normal for the past for July 13 to July 14. Okay. This data is usually obtained from the Advanced Composition Explorer. This gives us a real time, more or less, a real time data of the solar wind. An alternative data source or satellite that measures solar wind, which also aims to replace this mission, yung ACE mission, is the Discover satellite. So this is this is Discover satellite, Deep Space Climate Observatory. ito medyo luma ng satellite but they still produce solar wind data in near real time. And then this also produced, this is a bit new. Ang data nito 3 years old pa lang, I think, or 4 years old. But anyway, so that was how yan yung nangyayari sa when an event, let's say a CME travels through interplanetary space. Now, once the event reaches the magnetosphere, okay, so we can talk about now the magnetosphere. So basically, magnetosphere is just a protective bubble of the Earth that protects us from the steady influence of the solar wind. Okay, kung wala tayong magnetosphere, kung wala tayong magnetic field, the solar wind most likely will just swipe away our atmosphere, ending life on Earth. And I think that's one of the theories right now why Mars is like that ngayon. They say that Mars, the magnetic field of Mars weakened substantially, that the solar wind swipe away or swoop away the natural atmosphere of Mars. So kaya manipis ang atmosphere ng Mars ngayon. That's the current theory. Okay, so magnetospheres basically gives you the configuration of the Earth's magnetic field near and far away. So because of this configuration, the aurora are usually formed at the poles because of this configuration. Because remember, diba, sabi ko kanina, if a plasma is trapped in a magnetic field, they move around the magnetic field but along it. So just like this one. So if this is the direction of the magnetic field, so that those charged particles will move along this direction. So that's why meron tayong polar cups. So this region are entryways of the solar energetic particles coming from the solar wind. Okay, so as I mentioned earlier, this is the shape of the magnetosphere because the solar wind is pushing the Earth's day side and elongates the night side. In fact, to give you a sense of the size, yung boundary ng magnetosphere in front or in the day side is about 10 Earth radii, about 10 times the Earth's radii. But at the back side, it's about few hundreds. So ganun kahaba itong magnetotail na to. Tinatawag na magnetotail. On the sides, it's about 10, it's about 15 Earth radii from this point towards this. So ganyan yung size niya. Okay, anything around that, masyado nang exposed sa solar wind yung, let's say, if a spacecraft is beyond this point, that spacecraft is very much vulnerable to solar wind influence. Okay, so this is an animation on how the magnetosphere changes with changing solar wind. Kapag relaxing solar wind, the magnetosphere is also relaxed. If the solar wind is fast, the magnetosphere is compressed on the day side. Okay, so just like this airplane. Okay, so I will not go into the details of the parts, but the most important part here is that the configuration of the Earth's magnetosphere, a magnetic field, and with the combination of the three motions that I mentioned before, what will happen is that the particles that are trapped within the Earth's magnetic field is the one that causes the Van Allen radiation belts. So ito yung trapped radiation, particles is a radiation belt. Okay, so ito yung mga danger zone. These are points in space wherein there is a large concentration of energetic particles, and this is because it is trapped within the Earth's magnetic field. And what happens is that if a satellite passes by that region, that satellite may be exposed to high levels of particle radiation. Okay? So dalawa usually yung spaces niya, but there are recent studies that meron daw faint third layer in the middle of these two belts that come and go depending on solar activity and certain geomagnetic configuration and situations. So what's important here is that we can talk about this one. This is the model by ESA, and unknown to many, at the surface level, hindi pantay yung geomagnetic field intensity. In fact, we have what we call your South Atlantic anomaly. So this is a region where the magnetic field is very weak compared to the rest. So what does it mean? Going back here, because remember this configuration, this energy belt, is behaves according to the orientation of the magnetic field. So the consequence is that Van Allen radiation belts, or the radiation belts in general, are closer to the surface of the Earth at this region. Okay, so that's why yung kung ang radiation belt mo at this region is lower, stronger, is closer to the surface, if a satellite passes by, normal, tapos dumaan siya sa region na mababa yung magnetic, malapit yung energy, malapit yung Van Allen radiation belt. So that means during the span where this satellite passes through this region, it may be exposed to enhanced level of particle radiation. Now, it is being modeled right now that soon it will split into two with so that means this region will widen. That's the model. Let me show you the model. And then it will split into two, and then the intensity is lower. This is published here, no? South Atlantic anomaly. This line or this graph tells you the area. So the area increases. So the extent na magnetic field, extent of this area increases, but the intensity decreases. So in the future, this intensity, the protection that this area provides to this region is weakening. Okay, which is important as well. Fortunately, we are a bit far from that region. Okay, so hindi natin to masyadong concerned unless we have a space asset that passes by this region at this level. Okay, so this is the magnetic field of the Earth. Now let's go to the atmosphere. More specifically, my favorite, the ionosphere. So this is where most of my researches are. What is the effect of what happens to the solar atmosphere to our ionosphere as it travels from the solar surface towards the Earth's atmosphere? So if you want to talk about the ionosphere, we have to talk about the Earth's atmosphere. So we already know that it's composed mostly of oxygen, nitrogen, with some traces, and oxygen with some traces of other gases like carbon dioxide, argon, and others. Okay, and we also know that these constituents of the atmosphere have the concentration of this species of neutral molecules in the atmosphere changes with altitude. Okay, so in fact, sa ozone, for example, mataas ang concentration niya sa stratosphere. That's why we call it the stratospheric ozone. And then this is the density of the atmosphere. Now, we're going to compare that with the so usually the Earth's atmosphere is divided into several layers. You have your troposphere, stratosphere, mesosphere, thermosphere, and they are defined in terms of the temperature of the air or the atmosphere. And the temperature gradient and the inflection point. Inflection points, those are the poses, tropopause, stratopause, and the mesopause. And these are usually measured, let's say, by your usual radius. Now, because of the sun's energetic rays, X-rays, UV, and near infrared, so because of the atmospheric composition, some of this energy do not go far down the atmosphere. In fact, they are mostly absorbed, UV are mostly absorbed in the upper levels of the atmosphere. And that is because of the presence of these particles. The point is that the mixture of energy radiation coming from the sun and the density of the neutral ion and the neutral particles or neutral molecules in the atmosphere, this energy ionizes the atmosphere. Okay, so we call that the ionosphere. Again, this is the Earth atmosphere, so horizon, troposphere, stratosphere, proper atmosphere, and your outer space. Okay, and then what about the ionosphere? So when sun's rays ionize our neutral atmosphere, it produces ions. Because as I mentioned earlier, because the density of the atmosphere changes as a function of height, and the solar radiation changes as a function, solar radiation that enters the Earth's atmosphere also changes as a function of time. A combination of that will form these layers. The point is that when UV rays primarily interacts with neutral atoms of the atmosphere, they produce ions, a pair of positive and negative particles. These negative particles are your electrons, and the electrons is the one that we use to characterize or stratify the ionosphere. So that's why we have different layers of the ionosphere. We have the C, D, E, F1, and F. And the main regions would be D, E, F1, and F. And these are the ranges of the heights. Electron density in the ionosphere is a function of several things. It's a function of time of the day. Nighttime, because there's no energy coming from the sun, there's no sunlight, so wala mag-ionize ng atmosphere. So that's why during nighttime, mababa ang ionization sa ionosphere. During daytime, wherein there's a continuous bombardment of energy from the sun, na-form yung several other layers like D, E, and then yung F region is split into two, magiging F1 and F2. Aside from that solar radiation, time of the day, solar activities also affects the amount of ionization. Mataas ang ionization during solar maximum, mababa ang ionization during solar minimum. That's two. And because of the fact that the sun's energy, electromagnetic radiation coming from the sun, is not distributed well around the Earth. So that means the energy coming from the sun is received by different parts of the ionosphere differently. So that's why it's also a function of position on Earth or location on Earth. Of course, seasons will also affect the amount of ionization. So those are four. Meron kang diurnal, seasonal, solar activity dependence, as well as location dependence. So later I will show you ano itsura. Just to give you an idea, neutral atmosphere versus ionosphere and the Kármán line. So ito yung pinuntahan ni Brand, yung sa Virgin Galactic, yung billionaire, I forgot the name. Anyway, dito nagpunta yung Virgin Galactic at the edge of space. So there was a lot of debate about this. Di naman talaga yan sa space, etc. But officially, the Kármán line, which is defined as the edge of space, is located this area. Okay, so ionosphere is actually part of space already. So that's why a lot of space scientists are actually focusing on the ionosphere. And how important is the ionosphere? Because the ionosphere affects radio wave propagation. If there are changes in the ionosphere, communications using radio waves are affected. Communications from satellites, communications from the ground to satellite, communications from ground to ground, yung mga skywave, etc. Lahat yun may be affected depending on how the ionosphere behaves. Now, personally, okay, what I do as a scientist and as a researcher, my focus when I study the ionosphere is not the electron density itself, but the total electron content along this column, from the bottom to the top of the atmosphere. So I count electrons, not literally, but using special techniques. And we call that the total electron content. So the total electron content is a measure of ionization. It's basically the sum of all the electrons within that line of sight. We have a vertical TEC, so that's the number, the total number of electrons from the ground to up per square meter. Okay, as I mentioned earlier, electron density is a function of time of the day. So that means we expect that we have high ionization during day and have low ionization during nighttime. So this is an example of that, the diurnal variation. This is in UT time. 0 UT, this is measured from a receiver. This is estimated using a GPS receiver in Manila Observatory. 0 UT means 8 p.m. 8 a.m. So ito yung 0Z. Pag napapalipat tayo ng radiuson, ito nangyari. So 6 UT is about 8 plus 6, that's 2 p.m. local time. And then it will start to decrease, and then it will be at lowest at around 22 to 24 UT, which is about, before sunrise. Very, very peak ng midnight. Anyway, this is for one station. Now we can also do mapping. We can also look at total electron content on a certain region like this. So this is the total electron contents in the Southeast Eastern Asian region. Okay. And then at this region, it's about 7.5 total TEC units. Okay. And then when you go to 6 UT, much of this region are highly ionized, represented by high total electron content. And then when you go to 12 UT, so that's about that's 8 p.m. local time. That means that ionization will start to decrease. And then at 18 UT, it's very, very low at this same as level as this one, etc., etc. So this is your regional TEC maps. We also do this. We also have global TEC maps. Globally, it would look like this. So this is the global map at February 17, 2019, 8 a.m. local time, 0 UT. This is at local time 2 p.m. or 6 UT, 12 UT, and 18 UT. So you will notice that the region around the globe, the region of the Earth where there is high ionization, varies with time. It doesn't mean that the ionization moves, but this is because the Earth rotates. So when the Earth rotates, different part of the Earth is facing the sun. So more or less, you can look at this as this area is where the sun faces the Earth, or the Earth faces the sun, or something like that. Okay, it's not the plasma that moves, but it's a function of the rotation of the Earth. Okay, so we can do this as well. So actually, ako yung mga nag-graph itong mga. Now, what happens now if we have a CME that interacts with the Earth? So let's continue with our animation earlier. So right now, ito yung na-produce na CME, di ba? So it will now travel. So it will now travel. Ito yung CME. It will now travel the interplanetary space. It will first reach maybe the orbit of Mars, or orbit of Mercury, because Mercury doesn't have too much magnetic field, so it will just pass by, will not be affected. And then if and when this cloud of plasma reaches the orbit of Venus, and let's say it also hits Venus for some reason, no? At sila tinamaan, pati si Venus, it will also be like that. But when the Earth now meets that CME, this is what usually happens. Okay, let me just pause it like this. Okay, and then I will slow it down. Okay, so we know that this is the Earth's magnetic field, as I mentioned earlier. And let's say, this is one important thing. This is your cloud of plasma. It's a very, very large cloud. Hindi siya maliliit na cloud. Very large siya. That's why, relative to the Earth, the magnetic field line may look parallel. Okay? Now, for example, the magnetic field that this CME is oriented southward. So you can consider this as opposite polarity than the magnetic field of the Earth, because the magnetic field of the Earth at the equator is pointing upward. So pointing downwards is CME, pointing upward yung Earth's magnetic field. So what will happen? Just like when you have north and south pole of a magnet, they will attract. So once they attract, magnetic reconnection happens just like before sa sun. Nalala niyo, di ba? So what will happen is that the plasma contained in this region will now explode at that point, and the energetic particle that this CME carries will now enter the Earth's magnetic field, funneled through the direction of the Earth's magnetic field, and this forms the day-side aurora. Yes, meron pong aurora sa araw. Of course, di natin siya makikita because sunlight is much, much brighter than the light produced by the aurora. But not only this, because this CME is passing through the Earth's magnetic field, same thing also happens at the back. So yung magnetic field na nakat dito, kasi makakat niya yan eh. Yung magnetic field na nakat na na-form together with this interplanetary magnetic field, what will happen is that they will be swept towards the back of the magnetosphere. And there we have another magnetic reconnection. When that magnetic reconnection happens, the plasma that contains here will now be ejected again following the magnetic field lines. Remember, the particles move along the direction of magnetic field lines, and they will be funneled towards the night side, and that is where we can see the night side aurora. And that is what we can see in the nighttime. Okay, so that's how usually it forms. But more importantly, this phenomenon this is called a geomagnetic storm. It's a geomagnetic storm na nagkaroon ng abrupt changes sa geomagnetic field. And that is depicted by this illustration. Imagine, we have 4 geomagnetic field lines. Nung nag-interact yung electric magnetic field ni CME, naging 3 na lang. And then naging 4 na lang. So at the start, the magnetic field is actually compressed. When the compressed magnetic field lines, it will register as an increase in intensity. But after some time, it will start to decrease. And then after it passes by, these magnetic field lines will start to recover. We call that a geomagnetic storm. Okay? And because there are changes in the magnetic field, as I mentioned, several things will happen. There will be changes in the orientation of electron density. There will be induced currents because of the change in magnetic field. But not all CMEs can produce geomagnetic field, a geomagnetic storm. Another aspect is that the orientation of the magnetic field that the CME carries. Kaya tinitingnan natin sa solar wind data is the Z component, this component of the magnetic field, yung BZ. Pag nag-southward siya, tiyak magkakaroon ng geomagnetic storm. Otherwise, walang geomagnetic storm na mangyari. Kahit meron pa siyang malaki CME. Okay. Ito yung usual measure, DST, Disturbance Time Index. This is a measure of geomagnetic storm. So I mentioned earlier, at the start of your geomagnetic storm, magkakaroon muna ng sudden increase in magnetic field. We call that the sudden commencement. And so that's the start of the geomagnetic storm. Now, once the geomagnetic field interacts with the interplanetary magnetic field, it will start, the geomagnetic field will start to weaken. And this is depicted by a decrease in DST index. This is in nanotesla. So this is actually magnetic field measure. So this is the main phase. So this main phase is the time where the magnetic field of the Earth starts to weaken. Okay, and then after the storm has passed, or the CME has passed, the magnetic field will start to recover. So remember, the generation of magnetic field of the Earth is continuous by the Earth's dynamo. So ito yung recovery curve. So this is your typical parang anatomy ng isang geomagnetic storm. Meron kang sudden commencement, meron kang main phase, and meron kang recovery phase. Now, so this is one of the indices or parameters that we use to characterize geomagnetic storms. So kapag superstorm, ang DST less than 200, it is intense, but DST is between negative 100 to negative 200, moderate pag negative 50 to negative 100, and weak storm kapag negative 30 to 50. Okay? So as I mentioned earlier, meron yung highest class, yung strongest solar flare nung solar cycle 24, September 2017. It produced a CME. Okay? And then meron din tayong St. Patrick's geomagnetic storm noong 2015 March. And then comparing that to the stronger ones, this is how DST looks like. By the way, this DST data came from the World Data Center from Kyoto University. Okay, so this one is the September, the CME caused by the September flare. So it only reached about negative 100. So just at the boundary of your intense storm. Yung strongest storm for the past solar cycle 24, yung St. Patrick's geomagnetic storm, it reached about negative 200. So nandun na siya sa superstorm na to. Okay. Boundary na siya ng superstorm. So kakakross siya na sa superstorm. Pero nagkaroon ng geomagnetic storm noong October 2003. Because this is actually happened in Halloween, October 30-31. We call this the Halloween storm of 2003. Okay, this is so strong that it reached to about negative 400. Okay, negative 400. Now, yung Bastille, meron ding geomagnetic storm noong 1989. Umabot siya ng negative 600. Yeah, negative 600 nanotesla DST. So this is a very, very large, very, very strong geomagnetic storm. In fact, itong storm na to, actually, specifically itong storm na to, itong October 2003, the storm, it caused a widespread blackout sa Canada that lasted for a few hours. Okay, ito I think it also caused a blackout. Now, strongest on record was the strongest detected was the Carrington event, 1859, September 1 to 12. Ang estimated niya na DST is negative 1,700, more than pa. So we call this your Carrington event. And if this kind of event hit the Earth today, it will cost $1 to $3 trillion worth of economy. Not to mention the COVID and the effects of COVID-19 pandemic sa economy. So it will really put us to a very great danger kung ganitong klaseng Carrington class event. In fact, a few years ago, there was a CME that was produced. It was so strong that it could have caused the Carrington event if it was ejected a week earlier. If it was a week earlier, kung yung CME na yun na-eject a week earlier or a few days earlier, it will definitely hit Earth and it will cause a Carrington level event. Fortunately, it was late for a few days. So, yung CME na yun na sobrang lakas, na-miss yung Earth. Ito yung sinasabi ko kanina, it is a low impact, low risk. It's very, very few, very seldom nangyayari. But when it hits us, grabe ang impact. In fact, meron ng legislation sa there are already legislations on space weather contingency plans sa US. So ganun sila ka-invested sa space weather. I learned that when I attended the space weather workshop sa US a few months ago. Of course, online. No? Pwede pumunta doon na. Anyway, so yun yung point. No? Which countries, even poorer countries in the African region, in Mexico, even in Southeast Asia, they're starting to really invest on monitoring space weather for their own benefits. Now, another measure of geomagnetic storm is called your KP index. So, parang ito yung mga signal number natin, wind signal number based on winds yun, di ba? This is based on changes in the magnetic field. Okay, so this is not a linear data, but this is more of an index. The point is that KP index greater than 4, there's a geomagnetic storm happening. And this is usually measured by, this is usually used by countries in the northern and southern hemisphere to monitor their space weather events. Kasi iba yung effect sa kanila sa equator. It's like us. But the point is that, for example, yung NOAA's, yung geomagnetic storm scale, yung mga signal nila, is based on KP. Yung G0 level event, called the quiet and unsettled, KP values are 0 to 3. Kapag when it starts to be active, KP index 4. That's why yung nakita nyo kanina, yung geomagnetically active ngayon, because KP index is 4 kanina. And then above 4, 5, 6, 7, 8, 9, yun na yung meron ka ng storm. G1 storm, G2, G3, G4, G5. Minor, moderate, strong, severe, and extreme storm. Sorry, this is storm. Okay? And this is their measure on, they also use this to know or to estimate saan makikita ang aurora. So this is an example of that graph. Okay? So KP3, dito makikita yung aurora. Pag KP5, dito makikita yung aurora. KP9, makikita hanggang New York, etc. etc. Okay, KP more than that, maybe. The Carrington event, by the way, so strong, geomagnetic storm is so strong that there were reports na merong aurora na na-observe sa Hawaii tsaka sa Caribbean. Who knows, baka may nakita rin sa Philippines. We don't know. Okay, but that's how strong that event is. Okay. And this is the geomagnetic storm, the geomagnetic indices during the September 2017 flares. So during that time, yung KP index reached to 8. Okay, during this storm. Now, let us go back to the space weather effects on the Earth. Kasi yun yung title, no? Space weather and its effects of Earth. Physically, sa mga tao sa atin sa baba, wala tayong mararamdaman what happens. But we are affected because we are now starting, we are very dependent now on technologies. So these are some of the things that I am interested in doing research on, and I'm currently doing work on or have done work on. So I have students who are working on scintillation. So scintillation is an event wherein, diba, usually ang ionosphere is very smooth, but sometimes so under certain conditions, nagkakaroon to ng mga tinatawag na plasma bubbles. So yung plasma bubbles, para siyang bula sa tubig. So pag clear yung tubig, kita mo directly, may nakasulat sa baba ng timba, kita mo yung itsura ng timba sa ilalim. Alam mo kung ano yung nakasulat. Kapag nagkaroon ng bubble, di ba, pag nakita natin yung ilalim ng timba, kapag may bubbles yung tubig, hindi natin siya masyadong mabasa kasi nagkakaroon ng interference sa light. Ganon din kapag nagkaroon ng plasma bubbles. Right? Instead of having interference sa light, meron interference sa radio signal. So what will happen is that they can affect communications and navigation. So pwede magkaroon ng loss of luck. For example, minsan sa ways, di ba? Napapansin nyo minsan, especially sa gabi, sunset time, after sunset, sa makikita nyo, masasabihin ni Waze, GPS not found. So that's one of the manifestations of these scintillation events. Another thing is yung, let's say, total electron content. They can actually affect the accuracy of your position. Aside from signal reception, it can also affect quality ng signal. It can delay or advance our signal coming from your satellites. So what will happen is that it will induce positioning error. So I've done things, especially, in fact, yun yung isa sa mga topics ng dissertation. So all other interested things that I have there right now are yung how ionospheric currents will affect geomagnetically currents, especially power systems. And then other effects ng solar weather on radiation, on positioning, navigation, and communication. Okay, so what have we done sa grupo ko when after coming back from the Philippines, from Taiwan, from my PhD in my postdoc, when I went to Mapua, I started my group and started working on studying space weather, even without funding. So we started with the things that we can do. So what we have done so far is we are studying and we've been studying responses of the ionosphere to space weather events. And then dun muna ako, kasi yun muna palang yung capability based on my current resources. What is the response of ionosphere in the Philippine context to space weather events? Okay? So ano yung nangyayari sa Pilipinas, sa ionosphere sa Pilipinas kapag mayroong space weather events? But before doing that, I have to develop my own tools. The first tool that I did was to compute for total electron content based on local GPS receivers. So local GPS from NAMRIA. NAMRIA is generous enough to lend me some data from their GPS network, and I use that to measure or to estimate total electron content. Okay, and this was developed together with my first BS physics student, si Merlin Mendoza. By the way, si Merlin is currently on his master's program sa National Central University, taking up master science in space science and engineering. Okay, but anyway, aside from that development, we applied that to this specific storm, St. Patrick geomagnetic storm of Lake. So itong storm, itong CME na. Itong CME na. Okay? So first thing that he did, of course, we quantify the storm. First, we look at the solar wind and geomagnetic activity. Solar wind data. So solar wind speed, density, pressure, as well as the magnetic field, yung magnitude ng interplanetary magnetic field, and EC. So, monitor namin yung solar wind. And then we also monitor the geomagnetic indices, which will tell us kung kailan nagkaroon ng storm. This is KP index, I mentioned it earlier. This is PST index, I also mentioned it earlier. And this is another, yung AE index, which I also mentioned earlier. This is a figure. The point is that we started with how solar wind behaves and when it impacts. So yung solar wind data tells us kung kailan dumating yung CME. Geomagnetic indices tells us kailan nag-start yung geomagnetic storm. And from this, we calculated the total electron content and compared with your usual. And we measured it in 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 stations from Taiwan to Davao. As you will notice here that during the main storm, karoon ng increase and decrease in ionospheric activity, but only until until this area. But as you go down further, Legazpi, Tacloban, PTGO, and Davao, that effect in decrease in magnetic ionization was not felt here. That's because at this point, at this area, bababa yung ionization. But in next day, during the recovery phase, continues yung negative, tinatawag namin itong negative ionospheric storm. Okay? And then it was observed hanggang sa Davao until such time that the magnetic field of the Earth recovers. So this is just one of the examples of what we did so far. So this is solar wind, and this is ionospheric blast or total electron. I also did some work and continuing to work on positioning error of GPS. This one is during that X9.3 flare event. So there are, sa solar flare kasi meron dalawang effects. Meron kang primary effect, so that means instant. So remember, solar flares also produce solar radio burst. Kapag yung solar radio burst, merong component ng L-band o yung frequency ng GPS, it will interact with GPS reception. Okay? So instant yun. But there is also a secondary effect, which is yung kung ito man, kung itong CME na ito ay itong flare, solar flare na ito ay nakaproduce ng CME, that means pwede siya makaproduce ng geomagnetic storm. So this is an example of that effect. So nakita nyo sa height, positioning height, karoon ng degradation by 10 meters. Okay, so yung effect niya sa position. We also do, this is also the same content, same flare event, but this time we look at geomagnetic effects sa total electron content as well. So yung positioning error dito is actually produced by your increase in ionization. So pag nagkaroon ng increase in ionization, one of the main impact is yung positioning impact. So ito yung first ginawa. And then right now, isang estudyante doing his PhD is trying to do a map of EEC, similar to the map I showed you earlier. But this time we use the available GPS satellites provided by numerical. So this is an ongoing project. So what we aim here is we are looking at developing a regional PEC map for using these stations so that we have a more detailed morphology of the EEC around our region, which can aid or help the navigation community. Now, aside from this, we also did some studies, and I'm doing studies on ionospheric irregularities. So, pag nagkaroon ng plasma bubble, nagkakaroon ng fluctuation sa signal. And this may cause loss of signal, and this is due to plasma bubbles. So, these plasma bubbles can be observed using PEC using air glow images from an all-sky camera. It can be observed by GNSS receivers. It can also be observed by ionoson. It can also be observed by radar. These are special radars, no, different from the Doppler radars that we have right now. And then TEC mapping, which is what this guy is trying to develop. TEC mapping. Okay, and a student of mine look at that. Look at scintillation event during the geomagnetic storm in 2015. So this is the same geomagnetic storm. And what was discovered is that before the storm, there is a consistent presence of these irregularities in March, every nighttime, continuous yan. But when the storm hit the Earth, this scintillation event disappeared. Okay, because this is interesting because sometimes what happens is that in geomagnetic storm actually enhances these events, but this particular storm in this particular region, what happens that this events was suppressed. Okay, and we're still investigating why is that. Other ongoing projects or researches that I have. Sabi nga kanina, I'm doing solar flare effects on navigation. This is being done with a colleague of mine with RTU. Also, how ionospheric storms, will it decrease or increase? Will the increase or decrease of total electron content be affected by the time the geomagnetic storm starts? So we're looking at the preference of ionospheric storms based on time of onset of geomagnetic storms. So this is also being done with my student, with my colleagues RT. A student of mine are starting from in Mapua, starting to look into medium-scale traveling ionospheric disturbances. These are plasma bubbles that travel in a lot of ways. From a lot of sources. Sometimes they come from Japan. We would like to know if it actually reaches the Philippines. MSDIDs are also generated when there's a typhoon. So that means if there is changes in the ionosphere caused by this medium-scale traveling ionospheric disturbances, therefore any radio wave propagation this will be affected by that ionospheric disturbances, which may be caused by typhoons. So I have another student from Mapua who are looking at response of ionospheric response to solar eclipses, because remember that ionospheric electron density is a function of the amount of sunlight being shine on the solar atmosphere. So what will happen to the ionospheric, to the electron density if suddenly it is blocked by the moon? So we're looking into that now. Especially yung two recent annular solar eclipses natin sa nararamdaman sa Pilipinas noong December 2019 and in June 2020. So we are looking into that. Also, we are looking into development of a low-cost scintillation monitor. So yung mga Arduino-based na GPS receivers, which are very cheap. We are trying to develop one that will measure ionospheric scintillation as well. So from a cost of about 10,000-15,000 pesos, low cost, compared to hundreds of thousands of pesos of high-grade scintillation monitor. So we're trying to develop. And in connection to this, I have a student who are analyzing scintillation based on scintillation on L-band signal, which is important for GPS, as well as VHF and UHF, which is important for communication under different space weather conditions. So these are the things that we are doing right now sa mga colleagues ko from Mapua as well as in RT. And I'm mentoring these guys to produce these kinds of researches. So as one of the, based on the invitation, so one of the things that we would like to discuss later, if we have time, is maybe discuss some opportunities that we could explore later on for research collaboration, which I'm very much willing to do with Pag-asa. And it will be an honor to me. I will be working with Pag-asa, especially sa space science and astronomy section. And I list down here some opportunities that we may want to explore in the future, in the near future, in the far future. First, as I mentioned earlier, solar flares are produced by active regions. And most of the time, solar flares also produce solar radio bursts. So I'm interested in looking at the observation of solar radio bursts from solar flares using the country's own radio telescope. Similar to what I showed you earlier, it's a Lermont Observatory na solar radio flux. But I'm not really familiar with what kind of data that Pag-asa radio telescope can provide, but I'm very much interested in exploring this area. Okay. Next is sunspot identification and classification using machine learning techniques. So this includes, I don't know, from the picture itself, where are the sunspots that we can identify using machine learning techniques, and maybe we could also classify them magnetically if it is an alpha, beta, delta, gamma, or combination of those using machine learning techniques, because of the fact that we have a lot of data that is being recorded by Pag-asa. Okay. If I may ask, kailan po unang record ng sunspots? Drawing ng sunspots ang Pag-asa po? If I may ask, anyone can answer? Anyone familiar? 1960s? 70s?
Sir Marian, nakamute ka po.
Yes, Dr. Ernest, may data kami ng 1960s and above.
Yun, 1960s and above. So we have a lot of data, and we can actually, I think we can do this. We can put that data into a machine learning algorithm and allow the machine to learn how to identify this technique. So that's a possibility, no? This is something
Yes,
explore
Doctor.
later.
Doctor, yung classification na ginagawa namin dyan, meron kaming set ng classification ng sunspot from A to F. So,
Yes, sir.
So yung machine learning technique, I do not know, pero siguro later on na pag-usapan natin ito. But right now, yung aming ginagawa na kung paano i-group ang sunspot base dun sa rotation ng sun, isa namin ginagawa sa opisina.
Yes, sir. So, but the classification is done manually, tama ba, sir?
Yes, may manually namin ginagawa ang classification.
Yes. So maybe we could explore this thing now. We could put this huge data that we have and put it in a machine learning algorithm to allow these machines to learn how to classify and do this probably automatically. That's something that we could think about actually. No? Anyway, so moving on, we can actually also do some studies on geomagnetic and induced currents for using we have existing ground magnetometers. There are magnetometers in the Philippines that's operated by Magdas. Magdas is sa Japan, Kyushu Tech, I think, if I'm not mistaken, or someone from ISWI group. And then I think NAMRIA is also operating ground-based magnetometers. So this data coming from magnetometers can actually support research on geomagnetic induced currents, which I would like to explore. We can also do what we can also do is to try to establish in the long run an online dashboard for space weather products for the Philippine space weather community. So aside from data from NASA and from ESA, we can actually provide other data that we can actually produce ourselves. Total range of content from our own GPS satellites. Just like that's why we are actually trying to develop these techniques already from the head on when I went back. So this is one of my, so to speak, dreams that we also have some kind of an online dashboard for space weather products. That will be beneficial for Philippine users. We can also look into opportunities on how local weather, thunderstorms, typhoons, etc., or even earthquakes affect the space environment, because those are also being studied abroad. Typhoons na dumadaan sa atin, they can actually change the status of the ionosphere. So that's one, which later on can affect radio wave propagation with applications in navigation, aviation, positioning, communication, etc. And then if we already know how if we already study very well how these things, how space weather really affects the Earth, especially in the Philippine context, no, and then maybe we could dwell on forecasting space weather in the context of Philippines. Yeah. If I may ask, if you would allow me, no, I would have one of my dreams, no, na for the Philippines, for the space weather community sa Pilipinas, yung mga equipment wish list ko, no. Hindi ko naman sinasabi na bibili ng pag-asa, but this is some of the things that we still need in order to give us a good set of information about space weather status in the Philippine context. So primarily ionosonde, so this is very important especially for communication, especially for HF communications. All sky camera for air glow observation. I've already in talks with a Japanese professor who are currently developing low-cost all sky imagers, and they would like to, I don't know, he is offering me to put up a station or to deploy this kind of camera sa Pilipinas. Because they really want to know, yung all sky camera kasi ginagamit siya for monitoring yung tinatawag na MSTIDs. So they only have all sky cameras for air glow observation na hanggang Japan lang. And they want to extend that observation hanggang Pilipinas because they believe that this MSTIDs or this disturbances actually travel from Japan all the way to the Philippines. And they don't know until when siya dumarating sa Philippines or up to which extent. Of course, if you have a radio telescope, but I think yung radio telescope po natin only operates in two bands, L-band and I don't know isa pa, no? But what we can also do is to put up a spectrometers naman, so spectrum-wise. So a full spectrum of radio signals so that we can also know type ng type of solar radio burst, type 1, type 2, type 3. So these are some of the things. And these are the things, equipment that we still lack in the Philippines that Indonesia and Malaysia already has. And they are putting up, and they're also using that for their own space weather forecasting, especially in atmospheric forecasting. So that's it. This is my presentation. Sakto lang, no? 4:15. Thank you very much for your time, and I'm open to questions.
Wow, thank you again, Dr. Macalalad. I hope you all enjoyed this great presentation and we look forward for the opportunities. And we will now go ahead and take some time for the Q&A session. So this is your chance to personally ask your questions. So just raise your hand, state your name, and then ask your question. So to our participants, now is the time to ask your questions to Dr. Macalalad. Any questions?
Any questions?
Parang ganito yung klase ko no? Pag ako nagkaklase, walang tanong pag ako nagdi-discuss. So, it's either so sobrang walang naintindihan, walang matanong, or I don't know.
Okay, so we have a question from Mr. Mario Raimundo.
Dr. Ernest, I was overwhelmed by your presentation. Thank you very much for the presentation. Now, bago ko pumunta dun sa tanong, dun sa huli mo, dun sa some opportunities, gusto ko lang para magkaroon tayo ng maliwanagan mo din, yung observation of solar radio telescope na lalagyan mo na, may plano ka na maglagay ng spectrometer. Ang observation na ginagamit namin doon, na-determine lang namin doon yung parang radio flux, yung signal ng sun, yung intensity niya. Ang problema lang noon ay ang aming observation doon ay limited kasi masyadong mababa na yung hindi na niya, nahirapan na siya pumanik. So lumalabas ay 8 o'clock in the morning hanggang 10, and then ulit namin ng 2 hanggang 4 o'clock in the afternoon. So very limited lang yun ng time na observation ng sun. And then na-detect lang noon namin ay ang signal na kung saan talagang gusto ko doon ay ma-detect talaga yung solar flare na kung saan i-expect ko doon sa Gaussian curve na napoproduce namin yung spike. Pero nung ginamit namin yan, nung ginamit namin yun, hindi namin makita ang spike na yung changes in the flux.
Tama po.
Pag yung data ilagay namin, let's say sa Excel at produce kami ng graph, it is normal, everyday na lang ay gano'n na namin nakikita.
Yes. Actually, sir, one of the things that should be also considered kasi, talaga mahirap, sir, talaga, especially flares, kasi it's a function of kailan nangyayari. So it's kung ang opening lang natin is 8 to 10 in the morning and 4 to something in the evening, in the afternoon, kailangan yung flare mangyari at that specific time para ma-observe natin. And so far, because we still in the low solar activity, mababa pa rin yung solar activity, we really expect na wala tayo masyado makikita. But as the solar activity increases, so more solar flare events will happen. So that means we expect that there will be some flares that will be observed during those times. So yun yung talaga siya parang needle in a haystack. What we can do right now is just continuously observe, no? Kasi minsan I remember one time, no, may nakausap akong taga San Carlos, and then ang dinedetect naman nila magnetometers, magnetic activity. And usually they use that for earthquakes. Okay. Ngayon, there was an earthquake sa Negros, sa Bohol, di ba? A few years ago, 2015, 2014, mga gano'n, no, yung ball earthquake. Tinanong ko, may data ba kayo ng ball earthquake? Ay, sir, wala. Patay yung magnetometer. So, yun yung mahirap kapag pinapatay yung So, minsan nakakamiss tayo. Kung kailan pa natin pinapatay, saka pa tayo saka pa nangyayari. So, ang suggestion ko for radio telescope nga, talagang tatsagain lang talaga natin, sir, na I just hope that this data are being archived. Tama po ba? Na-archive naman siguro sila.
Yep, pero right now ay nasa maintenance ang kami ng nasira kasi yung nagpa-power doon, yung 3-phase converter. Pero ngayon ay ongoing na, progress na para maayos at ma-operate yung 3-phase converter.
Mm-hmm.
Pagkatapos ng Dr. Ernest ay yung tungkol sa kanina, no, nag-jot down ako dito, no. Maganda yung proposition mo na tungkol dun sa space weather. Sa Pag-asa, maganda to. Parang ang maganda siguro, nakikita ko rito ay mag-set siguro ng isang monitoring station na para dun sa tinatawag na solar flare detection, CME at solar wind monitoring. My question is, kung gano'n ang aming plano, let's say on a daytime activities na namin gagawin, at as a monitoring station, how many computers ang kailangan namin?
Sa ngayon, sir, wala pa akong idea, no, for that. Usually kasi, for example, if I can share my screen again, okay, I will share my, I want to share my entire screen. Okay. So dito ako sa monitor number 2 ko. Okay, can you see my screen?
Yep.
Yes po, yes.
Yeah, actually, for example, this is the Space Weather Information and Forecast Services ng Lapan. Okay? So meron silang forecast for solar, geomagnetic, and ionosphere. This is observation, by the way. And this is forecast. And then they have forecast for certain communities, etc. So this is a very basic page for this kind of data. There are more exotic, let's say, for example, sa Japan, of course, syempre Japan, they have, for example, this one, they have corona, so solar corona, they have all sorts of data na pwede makita. So some of these are actually, if you're going to, this one actually ay galing to sa, pina-download to ng Japan and nire-redirect nila sa kanila. But some, for now, no, what we can do, for example, itong kay SolarHam, ang ginagawa niya ay naka-piggyback siya dun sa data from SWIFT, for example. So for example, this data is actually from SWIFT.
So this is real time.
These are real time. Kasi real time ito, sir.
Okay.
Real time to real time. So may mga real time siya. So it's just a matter of, putting this. But although some of these are near real time, di talaga siya real time. So minsan may delay na 1 hour, maganon. But minsan kasi may mga depende sa data availability plus kung ano yung gusto lang nilang ipalabas.
Sa server siguro. Sa server
yes, so
siguro.
kung minsan kasi kung ano lang gustong ilabas ng SWIFT or ng iba, yun lang yung makukuha. But maybe in the future we could explore dealing with, let's say, NOAA or SWIFT or ESA to get their most available data, yung mga ganung bagay ba. So kung ano man yung available na data na pwede na makuha in real time na hindi pinapalabas in public in real time. So pwedeng ganun yung mga pwedeng gawin. So for example, this one are, for example, let's say, ito kay European Space Weather, Space Weather Service ng ESA, medyo pangit. So may isang, if you're going to look at Lapan, meron silang, ito yung mga data. So for example, ito, Solar Ghost. This is actually, if I'm going to copy the image link and paste it here, galing NOAA lang siya, sir.
Okay.
So ito ay image directly from NOAA. So may mga ganun sila. So ito NOAA, then LASCO. Ito yung spectrograph from Lapan. Tapos X-ray flux, galing din NOAA, SDO. Ito lahat to galing sa ano to. And then they have white light na telescope. They have spectrogram din from Lapan. And then ito yung I'm not sure kung ganito yung itsura nun sa inyo, pero sa pag-asa sa atin, pero meron din silang sunspot sketch sa Lapan, no? So yung mga ganun. So pwedeng ganito, no? We could start with this, and then syempre in the future we could improve the interface, we could improve the data, the preparation, and then we could also add our own data, let's say for the ionosphere. All these things are actually ionospheric data using Lapan stations. And we are, sa grupo ko sa Pilipinas, we are actually now developing itong S4 index, this Lapan TEC. We are already doing it. We are also doing this ionospheric TEC disturbance index. We are developing this. These things, FOF2, ionogram, these are from Ionoson. Kaya yung naisama ko sa mga wish list, no? Sa mga ganung bagay. No?
Anyway, so yun po. Dr. Ernest, more on sa research ang nabanggit nyo kanina. Pero sa bottom line kasi ng nasa isip ko, ay sa bandang huli ay minsan kasi mingi ng tulong sa amin ng NGCP. Yun yes, sir, kasi yes, ang National Grid Corporation, ang problema kasi nila, pagka ganyan may mga geomagnetic storm, bigla na lang bumabaksak ang kanilang mga substation at tumatawag sa amin. So, yes, makasakali na dahil dito, no? Nang sa pinag-usapan natin na ito, baka dito makapag-develop tayo para matulungan natin ang National Grid Corporation. Dapat siguro magkaroon ng formulation and then monitoring, a set ng monitoring station siguro para dito.
Yes, sir. Yes, sir. Actually, I have a student who are interested in doing research on that so that we know more about how geomagnetic storms affect GICs dito sa Pilipinas. Kasi iba ang GIC kasi sa Pilipinas compared sa, let's say, sa America or sa Europe. Iba kasi ang GIC sa So, I'm really looking forward dun sa idea na makipag-usap sa NGCP to discuss GICs. Kasi yun talaga isa sa mga... Yes, sir?
Count me in pagdating sa kasi dati ko na nakausap pang NGCP.
Yes, sir. We
Thank
could
you.
if we could I don't know, set up a meeting in the future, no, about that
Yeah.
to help NGP, especially ngayon, bagong solar cycle, so this geomagnetic storm will start to increase in frequency. So the monitoring such events will be very useful for NGCP.
Thank you, Doctor. Thank
Yes,
you.
sir. Opo. Willing to help po, willing to help.
Okay, we have another one from Miss Ramos.
Hi, ma'am.
Hello, Sir Ernest. Chat Ramos
Yes.
po from SSAS. So first po, we'd like to thank you for this presentation. Actually, this is our second. The first one is last week, a foreign astronomer from Romania. Uh, Totoo pong overwhelmed kami dun sa ginawa niyong discussion. And also, ang isang tabang puso ay yung mga opportunities that you presented. So, pangarap po namin yung space weather monitoring. Noon pa po yan napag-usapan. And siguro po may kayo yung mag-drive, yung mag-guide para maging in reality na lahat. So, siguro po magkakaroon lang po siguro kami ng discussion kung paano tayo magkakaroon ng collaboration regarding sa mga research that you have presented, kung alin yung magiging doable muna for the time being.
Wala po tayo. Sorry na wala po si Ma'am Kat.
Hindi ako narinig.
Medyo choppy yung line nyo po, Ma'am Chat.
I cannot, sorry. Ngayon,
Medyo may konting interference, Ma'am. Medyo sketchy. May ano po. Yung scratchy po yung voice po.
Sorry, ako po yung problema sa audio.
hello,
Hello po.
Ayan po, Ma'am. Mas okay na po yan.
okay na.
Ako yan. Okay po.
Ulit.
Hindi po. Sige po.
Ernest,
Pasensya
thank
na
you
po
for- Sorry po, ako rin sorry. Baka mamaya yung environment dito sa bahay ang medyo nag-cause. Thank you very much po dun sa what you have presented. Talaga pong, gaya nga sabi ni Sir Mario, nakaka-overwhelm siya. Yung iba bago. And then, talagang yung mga ibang gaps na fill in nyo. And also the opportunities to have what you have presented. So, dream po namin yun. Noon pa po yung pinaplano na magkaroon ng space weather monitoring. Kaya lang, syempre, hindi namin alam where to start. Kaya dun sa na-present nyo, parang nagkaroon kami ng nabuhayan kami to pursue that dream. Siguro with your help, magagawa na po namin to in the near future.
Opo.
And also, yung sa research naman, siguro po magsisimula kami kung ano yung talagang yung feasible, yung doable for the meantime, for the time being. Kasi hindi naman po ganun karami yung aming manpower
Yes,
para
po.
magkasabay-sabay po yung mga research na ginagawa.
Tama po. Yeah, po.
So,
Yeah, po. Actually, sabi ko nga kanina, sir, I'm very much willing to really contribute sa pag-asa in terms of this. Kasi actually, ako personally, since I came back from Taiwan, this has been my advocacy, no, to really improve and maybe make space weather to be as accessible to everyone. That's why kaya nga I'm very much happy nung na-invite ako ng Pag-asa to really talk about this. In fact, meron kaming naging proposal from for fishered funding sana before 2 years ago yata with RTU on yung dashboard na tinatawag namin. for space weather monitoring. But for some reason hindi nagmaterialize, no. We haven't have any parang dito, haven't had any response from PSHERD from that relative to that proposal. So maybe we could revisit that proposal and maybe we could present it to Pag-asa and see what we can do together relative to that dream dashboard na tinasabi. Tulad nung pinakita ko kanina na using lapat. So minsan talaga nakakaingit na sila meron tapos ba tayo wala. Kaya naman natin din namang gawin to mga to. So I'm really happy na open po ang Pag-asa to really explore these ideas that I presented. That's why I made this last slide, no, yung mga opportunities. And then ang current setup ko kasi with RTU is that NRCP funded me to mentor RTU. So what we're doing right now is some of that research topics that we're doing with RTU is under that program, yung RD lead program. So with that, ang hope po is makapacitated yung RTU to do research, and then maybe in the future they could do their own research. And hopefully, just floating my mind right now is maybe we could do the same with your section, with SSAS na section. And then maybe we could do some mentoring activities so that I could monitor research progress, which I think would be very helpful for both sides. I'm very much willing naman po na to really help any way I can.
Thank you very much. So parang talagang overwhelmed kami dun sa support na ibibigay niyo in case na
Yes, ma'am.
kailangan namin kayo. Thank you
Yes,
very
yes,
much, Ernest.
And so we have another one po for kay Dr. Nathaniel Servando po. Nats?
Good afternoon everyone, especially to Dr. Ernest.
Hi, sir.
Salamat kami for your very enlightening lecture actually. So tungkol doon sa research na sinubmit nyo sa PSHERD, siguro baka pwede kaming makatulong. We can kasi kahit pa paano PSHERD is actually our active partner, considering na we are in the same department. So baka makatulong kami, and we can start on that for our possible collaboration with your group.
Yes, sir.
Okay, may isang tanong na ako, Doc.
Yes, sir. Yes, sir po.
From your point of view, are frequent changes in solar activities are strong enough to have a long-term influence on the Earth's climate, or yung long-term changes in solar activities could affect the climate of the Earth to vary or change?
Okay, sir. Good question, sir. Actually, medyo inaabangan ko yung question na yan eh.
Alam namin yung mga processes involved sa climate system, but anyway, from your point of view, from outer space, di ba, beyond the Earth's atmosphere.
Okay po. Sige, sir. If I can share one slide lang po, no? If I could share, is it okay? Okay, sige. I prepared a slide before that. I was thinking kung i-present ko ba siya o hindi kanina. But one of the things that I've been asked before pa is how solar activity affect global warming. I think that's your question, sir, no? Tama ba ako?
Yeah, precisely.
Okay, sir. Well, kasi based on the graphs based on this data, no, before comparable yung effect ng solar activity, comparing the increase in temperature change, comparable yung effect or contribution ng solar activity to greenhouse effect, to greenhouse gases, even ozone, and maybe aerosols, volcanic and sulfates. But before, that's why nagkaroon ng Maunder minimum, there was a brief ice age during that time, tapos may Dalton minimum, etc. Because of that, solar activity really affects climate during that time. But right now kasi, the problem is there are effects, there are contributions from solar activity. But because of the fact that yung greenhouse effect, yung warming due to greenhouse effect, especially yung carbon emissions natin, talagang in-overpower yung contribution niya comparing it with the other contributions. So it's like, though sa current trend natin ngayon na increase in temperature, there are contributions from solar activity, but most of the warming is actually coming from CO2 emissions. So that's why kung meron mang effect from solar activity ngayon, nalulunod siya ng greenhouse effect. Kaya kung gusto natin siyang i-compare, wala tayong makikita ngayon. Before, maybe. But right now, talagang malakas talaga yung contribution ni greenhouse gases sa global warming. Kaya any effect ng solar, even ozone or aerosol, talagang hindi niya kayang, masyadong faint, kumbaga yung signal. Masyadong faint yung signal. So, yun po yung aking magiging sagot ko dyan. So, talagang masyadong malakas talaga si greenhouse gas na hindi natin makikita yung, kung meron man, hindi natin makikita sa signal masyado yung solar. Very, very faint to detect.
Yeah, okay. Thank you. Thank you, Doc. Actually, consistent din doon sa paniwala namin kasi sa lecture mo kanina, is more on yung high energy particle or
Yes, sir,
radiation ang affected rather than the low frequency or low energy like infrared. Kasi yung infrared ang mostly nagko-cause ng warming, di ba?
Warming po. Yes,
From
sir,
visible to infrared, from the electromagnetic spectrum of solar radiation.
Yes, sir. Yes, sir. Tama po. Yan po. So ngayon, sir, ang talagang effect ng space weather would really be more on the technology. Yun yung talagang effect. But for climate, parang sa ngayon, sir, parang talagang ang layo, ang hirap niyang i-identify. There were certain efforts already. Kinompare nila yung solar sunspots number sa preference ng formation ng typhoon during ENSO activity, but those are very even there medyo faint din yung signal na nakuha nila dun sa correlation between those two. So parang ganun. So that's why ngayon ako, sir, personally, I really focus on what really can be done right away na. Ano pwedeng i-observe, ano pwedeng ma-analyze based on local context. Yun po. Kasi sa ngayon, sir, talagang napakakaunti ang researches on space weather na ang context ay Philippines po. There were efforts before sa Manila Observatory, but for some reason, yung efforts sila for space weather research medyo nag-decline. Parang nag-focus sila sa other aspects. So, yun po.
One last short, any health hazard posed by these solar storms, if there are any?
There are po, but not on the ground. Mostly sa astronauts. Of course, di naman tayo masyadong affected. But for example po, if there is a flight that has a polar route, kasi minsan kasi pag dumaan sa poles, mas mabilis yung biyahe ng eroplano. But airline industries usually limit yung number of hours na nagpa-pass through yung eroplano sa poles, especially during geomagnetic storms. So pag may geomagnetic storms, usually ang airlines are given notice na magkakaroon ng geomagnetic storm and solar storms so that they could reroute their planes off the palayo ng poles. Kasi I think for every flight estimated loss sa rerouting na hindi planned na reroute is about almost $1 million yata or so per flight. Parang ganun yung nalo-loss. Yung nagkaroon sila ng cost-benefit analysis. So yun po yung mga health hazard. I think yung mga piloto na polar flights, I think, as far as I know, correct me if I'm wrong, meron silang monitoring device for radiation na nakakabit sa kanila. And then, limited lang yung flying hours ng mga piloto pag dumadaan ng poles. Parang gano'n. So, those are the health-related risks related sa space weather. But on the ground, not much.
Isa na lang, sorry, Julian. Among the research topics you highlighted, ang isang nakita ko doon na posibleng ma-consider ng PSHARED, ito yung, sinabi mo yung connected sa AI, Artificial Intelligence. Kasi right now, ang PSHARED may bagong program sila eh. Yung instead of manual, analyzing these sunspots, ito yung machine, which is synonymous to
Learning
AI, di ba?
Yeah. Actually, to be honest, sir, I have no experience in machine learning. No, it's not really my field, but it's something that I think is worth doing in the future. Because from the space weather workshop that I attended a few months ago sa US, one of the emerging research topics that is being done related to space weather is yung paggamit ng machine learning, especially for forecasting and then yung identification ng mga features sa sun. So they are doing efforts on that as well. But personally, I do not have any experience on that, but I think it's worth looking at, and I am willing to really help and learn with you in this field of research.
Thank you.
Ayan. So do you still have questions or ano? Talk na pala. Joke lang. So wala na po ba? So it looks like we have covered all our questions. Is there anything else you wanted to cover, Dr. Macalalad, before wrapping up?
Again, I would like to really express my utmost gratitude to Pag-asa for inviting me and giving me this opportunity to deliver this lecture. So I'm sorry. I apologize if it's a bit overwhelming, because to be honest, I'm a bit nervous on what to give to this lecture. So I just based my content dun sa invitation letter. But I really believe that this will just be a start of a good collaboration between my group, between me and Pag-asa Astro, and I am really looking forward to working with you. Hopefully, some of my students can visit, can have, can do collaborations with you as well. Maybe we could also do additional. Maybe my students can be exposed sa trabaho niya sa Astro, which I think it's not too really, hindi pa siya ganun kakilala. Kasi ako mismo hindi ko alam kung ano yung sort of space weather activities. So recently ko lang nalaman na meron din pala tayong solar observation. Then recently ko lang nalaman na meron tayong radio telescope. And I'm really glad that there are already efforts and there is already appreciation to this field, especially from a mandated agency like Pag-asa. So, yun. So, yun yung aking masasabi. And hopefully, I could visit the observatory soon after this pandemic, no? Sa Tanay. Kasi I also have some researches that uses radio sound for my other atmospheric research topics. So, meron din kasi akong atmospheric research topics. So, and my students are we really had plans na to visit Tanay Observatory, but tinamaan ng pandemic, so hindi na natuloy. But I hope really to visit the observatory and even the Pag-asa section sa UP to discuss more, or we can also do discussions via online and anything okay sa akin. But thank you very much again. Maraming salamat po.
Yay, sir. Thank you po ulit, Dr. Macalalad, for answering those questions and for a very great presentation. It was pleasure being with you today, and sana po talaga ma-meet namin kayo in person after this pandemic talaga po.
Yay. Thank you so much, Dr. Macalalad. We will now proceed with the awarding of the Certificate of Appreciation to our speaker, Dr. Ernest P. Macalalad. The certificate reads, Republic of the Philippines, Department of Science and Technology, Philippine Atmospheric, Geophysical and Astronomical Services Administration awards the Certificate of Appreciation to Dr. Ernest P. Macalalad in grateful recognition for sharing his expertise during the webinar entitled Space Weather and Its Effects on Earth, held via Google Meet on July 15, 2021, given this 15th day of July 2021. Signed by Dr. Vicente B. Malano, Pag-asa Administrator. Once again, thank you for sharing your knowledge with us, Dr. Macalalad.
Thank you din po. Thank you din. So, ulitin.
To our participants, you can now access the link to the survey form in the chat box. Please accomplish the form by 7 p.m. A certificate of attendance will be emailed to you shortly. Thank you for your time with us.
At this junction, we will hear a closing message from the Chief of the Research and Development and Training Division, Dr. Nathaniel T. Servando.
Again, magandang hapon sa ating lahat, lalong-lalo na sa ating resource speaker today, Dr. Ernest Macalalad. Actually, the first time I heard you about you, Doc, was from a friend, dating taga-Pag-asa, na he was doing his sandwich program sa Taiwan. Si Bernie De Leon, I don't know if you're familiar with him. Okay. At this very moment, we have reached the end of our event for today. A simple and yet worthwhile webinar titled Space Weather and Its Effect on Earth. A highly specialized and quite unique webinar, considering the past several virtual trainings we conducted focused on meteorology, like monitoring and forecasting tropical storms, climatology, and hydrology. In this seminar, we are listening about geomagnetic storms, ionospheric storms, and solar storms. Something siguro something new to us, some of the participants today. We in the R&D and Training Division of Pag-asa, particularly the staff of Space Sciences and Astronomy Section, headed by Ms. Chat Ramos, who organized this event, humbly express our utmost appreciation to each and everyone who took the time and the effort to be present in this virtual activity. To the participants, not just from Pag-asa, but students from Rizal Technological University and from the Mapua Institute of Technology. We hope everyone had a wonderful time and acquired new knowledge from the resource persons, from our resource person. Of course, to Dr. Ernest P. Macalalad of Mapua Institute of Technology, thank you for his wholehearted support by eagerly sharing his knowledge and expertise for us to better understand about space science, particularly how changes in the solar activity affect the Earth's weather and climate. We truly appreciate your insights, and I hope our SSES personnel will be inspired and encouraged to undertake researches in this field. Because under the Pag-asa Modernization Act, we need to strengthen our R&D activities, focusing not only in weather, climate, and hydrometeorology, but also in space sciences and astronomy. We hope this event will not be our first and last engagement, as we would welcome any collaboration with your group. Not in the future, but maybe soonest, no? The way nakikita ko sa mga kasama namin, they are really eager to do research after hearing your lecture today. Lastly, I would also like to express our thanks sa support ng Pag-asa Management, headed by our Administrator, Dr. Malano, and Deputy Administrator for R&D, Dr. SP Kayanan, and of course, Dr. John Dalida, our Deputy Administrator for Operations and Services, who delivered a welcome message earlier. Thank you, and wishing you all a pleasant and safe afternoon. Looking forward to our next event with you, Dr. Ernest.
Yes, sir.
Thank you very much, Dr. Servando.